Wacky Wednesdays. How's everyone doing this morning? Everyone having a good morning? I've got my Red Bull. Not going to knock it over today. That happened at the very end of yesterday. But how is everyone doing? How are you doing, Brad? Brad Nartology. Alexa, good to see you here. Good to see everybody in the chat. Let's keep going right here. Great. Awesome. So good to see everyone in the chat. So good to see everyone in the chat. And it is the start of class. Got your Red Bull? Like I'm starting to trend here. Red Bulls in the morning. Awesome. Well, with that said, we're going to start up with the material we ended off with yesterday. What we ended off with was outliers, influential points, and we're going to get to extrapolation. So I can't even speak this morning. But with that in mind, what are outliers? What are influential points? Well, there's two key characteristics, and for 100 points to start off the day, what are the two things that something must be extreme in for it to have influence? What are the two things that something must be extreme in for it to have influence on the regression? Who can tell us the two things that something must be extreme in for it to have influence on the regression? Make sure to be writing these down, and you should have definitions of both of these. Pretty much residuals and leverage. James, I'll give you the points right there. That's pretty much it. We get more specific. Connor gets points too. We get more specific on the residuals. There go Mila also. Mila and Grant, and Mila says studentized residuals. Now we're very, very specific because we call them deleted studentized residuals. So remember what a deleted studentized residual is. Watch yesterday's lecture, and I went in and I put all the timestamps in all the previous lectures. I was even able to do it for yesterday's lecture. So I try to update these. I got a little bit behind once again, but all the timestamps are in for previous lectures telling you what material's in them. So use that to check it out. I mean, you can use it without the timestamps, but I like for there to be the timestamps so you can kind of go through and get all the updates and see like, okay, we covered this, we covered this. You can also put in more timestamps. If you add a timestamp to the video description, I'll try to add it to the video lecture. You can be like, hopefully give me a time period from when to when I cover something, because then I can kind of block it off, be like, delete studentized residuals. So while you're studying, and that might help out other people, and I'll get 50 points if you drop those in there. So if you're watching this later and you're not getting points during class, you can always drop in timestamps. That helps us out. Put those in the comments on the videos. So we should know what these are. Make sure you know what leverage is. That's how far something is away from the mean of the x's. And make sure you know what deleted studentized residual is. A deleted means we remove the point, so we do not see its influence on the plot. And then studentized means it's been standardized, so it's a t-score. And then residual is how much it misses by. So you can see this point has really a lot of influence, and that's its deleted studentized residual from the black line. That's its deleted studentized residual. Streamlabs, you better be awake. Might take Streamlabs up to 5 minutes to wake up. Streamlabs might be getting his Red Bull right now. We'll find out in a moment. So, Streamlabs, what do we pay you for? Well, we don't pay you, Streamlabs, so. And so here we are at the influence plots. Now with influence plot shows us where the influential points are. And the influential points are going to be in here and here. First person 100 points. How many influential points are there? How many influential points are there? Ah, man. Nope. No one's got it yet. 0. Brad's right. Brad's got the 100. We're just doing 100 points. We'll do 300 points today. I know I can't change it up. I have the half. It's so close on this one. It's so close. But that's not an influential point. How do you know if it's an influential point? It'll have the X in it right there. That's how you know how it's an influential point. So there is one influential point, and this gives you the row it's in. So this is the influential point right here. That's the influential point, and that's the influential point, and that's the row it's in. Does that make sense on what this output's showing you? Let me move the mouse away from it. But that's the row that the influential point is in, and then it puts a star on it. So it was super close on those other ones. The size of the circle is the size of the influence. So I think it's debatable. Sometimes you can be like, well, that point right there is really big, and that one's really big. They have big influence. But the way in which this is deciding is it needs to fall into this quadrant or this quadrant, and that one just barely does not fall into this quadrant. It's like if its center was like right there, but not right below that. It's so close. I mean, it's like, someone could be like, yeah, that's influential, and they could also say that's kind of influential, but this algorithm we use right here, only it has to have leverage that's beyond this equation. Don't worry, we'll never solve this equation. This equation just dictates where, let's see, so it's considering the point as part of the quadrant above. Yeah, it is. Yeah, this point right here is considered part of this quadrant above right here. So it must have a center. So wherever its center is, that's where the point is. It's not that it goes over that line, it's where the center of it is. And then its influence kind of radiates out from it. This line right here is the high leverage line. So that's what's considered high leverage. And that is from this equation. So that equation right here dictates where this line is right here, which tells us where high leverage is. So if it's not in the quadrant, then we keep it in. Well, and so we will never just, Greg Kreshner, Brad, and Dennis, 100 points each. You'll never just throw it out. You'll never just like toss out the point. You'll toss it out if it's wrong. And so you're like, I know you guys were working on the assignment yesterday. The reason we toss out row 337 hints for the assignment is because it's miscoded. It's bad data. So you can remove bad data, but you don't remove just like, you don't remove data you don't like. So you don't remove data because you don't like it. You can remove data if the data is like entered in incorrectly. So entered in incorrectly. So if it's just wrong data. And the gray circles are ones that have just very little influence. So you can see these little tiny circles right here. A lot of them have very small deleted studentized residuals, and a lot of them have very little leverage. Like these right here are like a small leverage area. So the further it is over here, the less leverage it has. And the further it is outside of here, the more deleted studentized residual it has. So these points right here, why are these points right here not influential? Why are these points right here not influential? They don't what? These points right here were not defined as influential because 100 points, who knows? We should be able to pretty easily say those points are not defined as influential because, here's a hint, they have very large, don't have enough leverage. Mila right there, you're perfectly right. They don't have enough leverage. They're close to like the mean of the x's, or close enough that we're not defining them as influential because of that. And so we have another plot right here. This point is ridiculously far away. This point right here is like somebody who, let's say, weighs 500 pounds and is 8 feet tall. That's ridiculous. They're very far away. But you know what? You know what's interesting? They're right where the model would expect them to be, basically, because the model gets their prediction very, very accurate. So they have tons of leverage because they have very unusual x's. Does that make sense what leverage is? It's how unusual your x's are. That person is very unusual in their x's, but they're right where the model would expect them to be. Maybe they're 8 feet tall and like 200 pounds. Their combination of x's is not what we would expect. I should have went like the more unusual route with the x's. They have a very unusual combination of x's, and we would not expect them to be there. And we can see kind of how this looks, because if you were to be like right here, if x1 and x2 are height and weight, this would be somebody who's like 160, 5'8". I'm trying to think, well, for males and females, maybe 5'7", 150, something like that, the average for everybody. So this person right here would be the average person. And then this person here is kind of extreme in some values, but this person is ridiculous. They're the person who's like 8 feet tall and like 200 pounds. Like, well, 200 pounds is kind of heavy, but for 8 feet tall, it's not. And this is not X and Y. We're not predicting height and weight. This is the combination of their X's. So leverage is when you have an odd combination of your X's, or you're just extreme in one X, because it can be like one variable. So if you were to look at somebody's leverage on just a univariate plot, they'd be unusual in one characteristic. Does everyone who thinks they understand how leverage works? It's like how unusual your combination of X's are gives you more leverage. It makes you more influential. More leverage means more influential. It's one of the two key components. And I'm going to draw one thing real quick that I think helps. This is not a mathematical equation. You're like, well, why are you drawing it? But I've always thought of influence the following way. Do not think of this as an equation. Streamlabs is going to be awake right now. Watch. Streamlabs, do not disappoint us. This is your moment, Streamlabs. So influence equals leverage times deleted studentized residual. Let me turn on the background. Let me do something right here. Watch, it's going to do it while I'm doing this. Maybe I do have to click the buttons. It's supposed to be on because I'm in Streamlabs OBS, But I did all these changes yesterday. I tried to get everything fixed up. It says get started. I've already been started. CloudBot is now on. It says don't forget to mod Streamlabs. Streamlabs, you better be a mod. How would you not be a mod anymore? Maybe they might have changed something in Streamlabs, because when I logged into Streamlabs, it said don't forget to mod Streamlabs. It is a mod. I'm very sorry. It says CloudBot is on. I got a message saying don't forget to mod Streamlabs. Streamlabs loves messing with us. If not, I'll give you guys some big points, but let's look at this equation right here. Influence equals leverage times deleted studentized residual. Now, this is not something you'll ever solve, but if something has no leverage, it can't possibly be what? If something has no leverage, which would look like the points, if it has no leverage in the univariate sense, it could not possibly be what on the slope? If it has no leverage, it could not possibly be what? If it has no leverage at all, it could not possibly be what? I won't do this. Could not possibly, it would be not be influential. Cannot be, Alexa, 100 points for there. Cannot be influential. Streamlabs, need to wake up. Give Streamlabs another 5 minutes. How would it get unmodded? They might change their bot or something. It might have been like an update. No leverage, no influence, which means it can't influence it. No deleted studentized residual, no influence. So if you were to say it has no deleted studentized residual, which would be points directly on the line right there. So now we're looking at this graphic right here. Then those points right there do not have high influence. The smaller the deleted studentized residual, the smaller the influence. So key thing we should know, how those two change the influence of a point. So the two things right there are leverage and deleted studentized residual. And sometimes you get so many of them that you just get tons of rows right here. These are all the rows that have undue influence. And we say undue influence, like too much influence. So all of these points right here have too much influence. Now, these aren't the highest leverage points. We got 2 points over here with ridiculous leverage, but they didn't have enough deleted studentized residual for us to say that they have undue influence. You can get a summary of these points. This is in your assignment. Do not just throw away these points. Do not take the points and throw them away. Make sure you take the points, look at them, and see what's going on. Talking about points right there. I wonder if I was hearing the points. But look at the points, see what's going on, and see if you can tell like why the points have undue influence, which is in your assignment. I went over it yesterday during office hours, so make sure to look at that. Extrapolation is a pretty easy topic, pretty nice and fun right here. Streamlabs, talking about fun. You need to wake up, Streamlabs. So extrapolation is when you go outside of your what bounds of what variable. When you go outside the bounds of what variable. I like to call it extrapolation. Extrapolation is when you go outside the bounds of what variable. Extrapolation. Let me look at that Streamlabs thing. It says make sure. I'm looking at one thing in the background here. The Streamlabs is a mod. Did it change? I don't know if it changed. That's so weird. The X variable, you're right. Wow, I come back and everyone's saying it. Nice job. We're gonna say Streamlabs is working. Why would you do this to us, Streamlabs? Wake up, Streamlabs. So it's when you go outside the bounds. What is a good reason to throw out a point? Streamlabs. I knew you got me, Streamlabs. Everyone's gonna take the points now. I have no idea why Streamlabs takes a while to wake up. It's doing its thing. It's getting it. It got coffee and Red Bull this morning. That's why. Everyone knows that's why. Streamlabs likes coffee and Red Bull, and it woke up. So what is a good reason to throw out a point? Bad data. Not like bad data you don't like, Nicole. Nicole, 100 points. Thanks for asking. But data that is like coded incorrectly. Like somebody misenters stuff and you just know it's impossible. Like we've had people who tell us they drank 13 days a week. You can toss that. So if someone says I drank yeah, if it's like not or you have variables, Philip, 100 points, like you could, well, you wouldn't toss the data point. You wouldn't use the variable if the variable is redundant information. Like you wouldn't include the variable in your model. And that's not like tossing data. That's just like not including variable. But good point. I agree. You wouldn't use redundant variables in a model. But you can toss a data point if it's just wrong. Like if someone says they drink 13 days a week, you're like, well, Brian said we can't toss data. You can toss a data point that's just impossible. You can't drink 13 days a week, so we can just toss it out. Bye-bye. Your data doesn't count. But it's not because we don't like it. It would kind of mess with our model probably. It's because it's not real data. So if you know something's bad data, you can toss it out. People get confused on units of measurement. Those numbers that have huge leverage but no deleted student are still to basically do the same thing as extrapolation. That's kind of the same thing, Brad. And Brad's great, Brad, 100 points, because you're kind of going into the extrapolation. When we talk about extrapolation, we're going to have a problem with extrapolation that the standard error is going to get larger the further out we go. So the standard error depends on the leverage, which is how extreme something is in its x's. What is standard error? 1,000 points first person. You have to say the word I like for standard error. And it's not. It's not that word. It's the other word I love. Brennan right there, you're right. Brennan got it first. Nice job, Brennan. It's uncertainty. So we see this with extrapolation, that we have more uncertainty. 100 points, everyone else. Thank you very much for that uncertainty. We should know standard error is uncertainty. And when we make predictions based on something that's an extrapolation, we have more and more uncertainty in what we are predicting. So we'll have more uncertainty in these predictions, whether it be for an individual or for a combination of x's. We're just going to have more uncertainty. So if the combination is very odd, cool. So this right here is, once again, where we'd have the least amount of uncertainty here. But here's the problem we run into. Is checking influence a way of cleaning data for use? We wouldn't, it's a way of seeing if your model is not being overtaken by a few points. So checking for influence would be a way of saying my model is based on the data it's created from, and there's not a few points that are dictating the model. And I think we saw a model that really exemplifies that with like the second example. This one has a point that has really strong influence on it, and this one has a lot of points that are like influencing it. I think if you have like 1,000 data points, you don't want one point, because look at this one point right here has the influence of like all these points in here. So this point right here in the model influences it as much as like all of these points in here, just this one point. So you don't want, this is why we say QQ straight enough, no outliers. We don't want one point to be the point that kind of makes our model. And without that point, the whole thing would change. Because imagine, if we hadn't collected that one person, this would be a completely different model. So you wouldn't, once again, you wouldn't toss this person out, but it means that your model is kind of being dictated by that point. And if you were to move that point, it would drastically change your model. So will your model actually work? Is your model a good representation of reality? Maybe. And so you're like, I don't know. I don't know if my model is a good model, because if that point wasn't here, I'd have a different model. So then it's like your model might not generalize well to new data. Your model might not be a reasonable reflection of reality. And that's what we don't want. We don't want a model that is dictated by just by like a point or a set of points. We want a model that is like based on the whole data. Great questions, Brad. 100 points again. Like that's what we want to be thinking about. Like, what does it mean that we don't want undue influence? We don't want points that kind of create the model, that our model would be based on just like these points make our model, and these other points, they don't really do anything. So that's exactly it. This is right here a point that is an extrapolation. But wait, tell me this much. If this is somebody's height and weight, and there's very little variation in the weight down here, do we have any points that are in the 122 to 130, 122 to 123 range? Do we have any points that are in this range? Aside from this one point right here, do we have any other points that are in this range? Do we? Yes or no? We should know that. Do we have any other points that are in this range like this point is? Well, and yeah, and don't worry, like this range right here I'm talking about, like this range. We do. Do we have any other points that have heights that are in the range that this height is in, like similar to this? Do we have any other points that are similar to this? Are there any other points for the x2 variable, which we'll just call height? We do. But do we have any that have this combination? No. That's what makes it an extrapolation. And this is the hard part about the multivariate extrapolation. Like, we understand what extrapolation is it's going outside the x bounds, but now it's an unusual combination of x's that we don't have data in. So an extrapolation is more of a degree now, because like, what does it mean to extrapolate in the multivariate sense? It means we're outside the bounds of the x's that we have, and we're doing something far out. So we think of extrapolation as like a degree. And this is a key thing right here, the extrapolation check. So extrapolation check is going to tell us how close we are to the mean of the x's. So the mean of the x's would get a 0. So let's look at a plot right here. If we did an extrapolation check on this point, we'd get 0. If we do an extrapolation check on this point, what do you think we'd get? Extrapolation check on this point, how far out are we out in this circle? If we were to go out further and further and further and further, who's got a guess on this one? What do you think we'd get for that, for extrapolation check? How far are we out, going out from the center of that cloud of x's, which is the mean of the x's. That's the center of both x1 and x2. It's the mean of the x's. So how far are we out? Well, remember, it's going to be like a percent. It's going to be percent. 100 points, Henry. Good guess right there. It's going to be a percent. What percent are we out? What percent are you like radiated out? A little bigger. I'll get Nicole, 100 points right there. Good guess, 15. Watch it be 15. You're right. I would say someone's really got another guess. Like, we're radiating out. 20. Everyone's saying I think it's like 30. I think it's like 30. We'll look in a moment. I don't want to cheat. Yeah, like 30 and maybe 50. Maybe I'd say 30 to 50. How far are we out on this one? Now, this is radiating out. And what do I mean by radiating out? Imagine that ellipse just radiates out, like it's going to radiate out. So how far are we out on this one? That point right there, how far are we radiated out on this one? Well, we can't go above 100. People are saying 90%, so we're going to say this one's 30. We're going to say this one's 90. And then how far have we radiated out on that one? How far is that point radiated out on this one? Which this one should be the obvious one. How far is that point? It's the same distance this one is away. Like, they're the same distance. 100%. Yeah, I think you can get the 100th percentile because it's beyond 100% of the data. It's like 99 or 100. That's going to be extremely. And here we are. So these were the right answers. If you're wondering what are the answers, those were the answers to how far those are out. So if you can see here that the 45 represents that we are 45% out from the center of this, not like a distance, but like if we were to radiate out with a kind of, you get Nicole 1,000 points. Nicole, and yeah, I see it right there. Great job, Nicole. You did yes 93. You're totally right that this is like the 93rd percentile radiated out. Amazing guess, Nicole, right there. And this is the 100th percentile. It's beyond 100% of the points when you radiate out. This is like 43 if you were to radiate out. We're not saying like how far you're out distance-wise, because these are the same distance, like this and this are the same distance away. But when you look at it as though like a radiating out, you guessed 43? I think you did, right? Great job. 1,000 points right there, Ben, also. Following along, making some good guesses. Wait, did you? Try to see if you did or not. Wait. You get 100 points for joking, Ben. I like it. Is the percentile based on the center to the furthest point or the edge to the circle? It's like the center of the point. Yeah. The center of the point to this right here. That's how it's calculating it. It's calculating like what percent of points are within like a density of it if you were to do an extrapolation. So does that make sense right there, Brad? Like, it's saying if you were to make a new ellipse going around like right here, then this new ellipse at the red point, which I wish we put an ellipse right there, would contain 93% of the points. Like if you made a new ellipse at this red going out from here, the new ellipse would contain 93. If you made an ellipse here, see none of it. It would contain 100% of the data. There's no points that are further out if you made an ellipse. And this is kind of the eigenvectors and eigenvalues of this for the math folks. It's like the dimensionality of it, because you can notice going the eigenvectors and eigenvalues are orthogonal reorientations of the data. And we can see here that in this orthogonal direction, it's a lot tighter than this orthogonal direction. You don't have to know the mathematics on that. I've had to do it before. It's not fun. But you can see that there's less variation in this orthogonal direction, just mean 90-degree angles, and then there's more variation in this one. The first point is 100 points away and everything, the distance, percentile of the distance. Yeah. This point is the furthest point away, and it's not because of its distance. It's because in terms of like an ellipse radiating out, that would contain 100% of the data. But this one, which has the same distance, if you were to radiate out the ellipse this way, you would still have points further out. Does that make sense? Like these points, if you were to radiate this ellipse out, you would still have points down here that are further out and points over here that are further out. So that's why this would only contain 93% of the data if you radiated out on this way. But if you radiated this ellipse out till it finally reached this point, you would have, you see if I'm radiating it out, it's going to contain all the data. Yeah, just keep thinking about the visual that it's this ellipse radiating out, and it's what percent of the data would be contained. And obviously, this is the mean of the data, so this would not be an extrapolation at all. So the extrapolation is seen as a percentage. Like when we talk about extrapolation right here, we're talking about like to what degree are we extrapolating? And when you extrapolate to a higher degree, what happens to your predictions? Your predictions would have more what? The more you extrapolate, the more you're going to have more this. It's not the highlighted word, it's the other word, which I mean, it is this word, but the more you extrapolate, the greater your what's in your predictions, which we'll use the predict function for. The more you extrapolate, the greater your what in your predictions, which is why we don't like extrapolation. I mean, you have to in some disciplines, but as a general rule, extrapolation is like, well, you're adding in a lot more of this. And we see it all the time. Like, I love talking about the time series models. Let's see, people should get in the chat. Time series climate change forecast. It's built in to the models, and they're showing it right here. So they are showing right here exactly what we're saying. And I mean, it's not a bad thing. Uncertainty, Brad, 100 points right there. You're totally right. This is not, we're not saying they're wrong. You can just see the greater uncertainty as you go out into the future. As you predict further out into the future, the models have greater uncertainty. So further predictions out into the future regarding climate, but we do see an upward trend in climate. So, and the models aren't wrong. It's not saying, oh, these models are wrong because they have more uncertainty. No, it's just a greater interval. It's a wider interval. So that's how we, in statistics, counterbalance going out into the future. We add this to greater, and look at how far out the interval is, because we're predicting like 80 years into the future. When you predict 80 years into the future, you have a lot of uncertainty, which is calculated via the standard error. So when people say to me, well, how can you make this guess 80 years in the future? I'm like, well, one, you got to look at the confidence interval, and two, it's just mathematics, and mathematics doesn't care about it. Just mathematics just does. It does what mathematics do. So I don't know. I like all of it. I like all the predictions. It's fun. All the data. So this topic right here, we do pretty quickly because this topic right here is about the most impossible topic ever. When I say that is because this topic could win you tons of money. Let's look at where it won somebody money. So we've got right here, we'll do the slide that. So what is a variable creation? The idea of variable creation is taking the variables you have and making new variables from the variables you have. First person to put that in chat, $1,000. 1,000 points, not $1,000. No, that's all for in jest. 1,000 points. First person who puts in the chat that creating new variables is just making combinations of your old variables. That's all it is. Variable creation. Philip, you get 1,000 right there. I like that reaction. Was everyone? If everyone did it, no, I'm just kidding. $1,000. Dennis gets it right there. Creating new variables, just making combos of your old variables. Yeah, that's what we're talking about. I love it when I see the typo because then I know someone was typing really quick. They're like, I love it. Sorry, Dennis. So $1,000. But what we have right here, and great job. That's one of the big things you just need to know about variable creation is you can literally make these combinations like, you could predict right here using the variable height times weight times circumference times density could be its own variable. So you could have your own variable right here where x is just the variable of this combinations. And then this would have a coefficient. Like you would collect some things height, circumference, density. And then, I didn't see that, Brad. And so The new variables right here require what we call domain knowledge. What do we mean by domain knowledge? Like, my brother's a pharmacist. He's going to make better variables for pharmacy than I will, because maybe he knows something like it's the nurse to doctor ratio, which explains how well a shift goes. Like, you need a certain amount of nurses per doctor at the hospital, and there's a ratio you should have. And maybe we see this like nonlinear trend that you see an increase in efficiency up to a certain point and then a decrease in efficiency after a certain point. So maybe my brother knows like, okay, we need a 3-to-1 ratio or 2-to-1. I don't know. Like, he would know these things. I wouldn't, but he might divide like the number of nurses that are the number of doctors on the shift by the number of nurses, or it might be vice versa. Just like whatever the ratio. I see. I don't know if there's more nurses or doctors. I don't know which way it goes, but he's going to know this right here. You guys are awesome in the chat. I love it. Everyone who just spoke right there, 100 points. You guys crack me up. I love all the jokes. So we have right here a Kaggle problem. And Kaggle, have we shown Kaggle yet in this class? Have we shown it yet? Because you can go to Kaggle and you can make money. Now, everyone's always like, Brian, why don't you go to Kaggle and just get rich? I'll tell you why in a moment. It's a good question. Because I want to go to Kaggle, get rich. Ooh, we got a. Wait, is that spaceship? Did I add that spaceship? Kaggle had that. I thought I put a spaceship in here. I was super excited. So let's go right to those compete. Let's go right to the competitions. $50,000, $50,000. Estimate the units of sales at Walmart. 6 days to go. 5,000 teams. I mean, that's pretty good odds for getting $50,000, 5,000 teams, and you get $50,000. So uncertainty, estimate the uncertainty. Ooh, looks like we got some variation, some standard error, some standard deviations for Walmart sales. And right here, where's the prizes? Show me the prizes. Rules, data, notebook, discussion, leaderboard. What? Is that their... Oh my gosh. Have they already made perfect models? Oh my gosh. And there's one person on this. He's got 68 entries. They might just be, there's ways to get perfect scores in Kaggle, but there's even if you have a perfect score, you have to like submit other stuff. Where's the prizes? Overview, prizes. There's the prizes. So Kaggle has become the main competition site for doing stuff like this. And here's all the different things right here. Multi-scanner, normative age and assessment, prediction with brain function structure and connectivity. I do not understand these things. I do not know that. Cornell bird call identification. Oh, you can get $25 for working with birds. So build tools for bird population monitoring. 131 teams. That's pretty cool right there. I know, right? Yeah, you can check this out. Oh, that's a cool bird right there. Do you hear birds chirping out your window? Over 10,000 bird species. Look at that cute little guy right there. So yeah, check it out. Check out Kaggle. Really cool site. And let's hop back right here so we understand what's going on with Kaggle site. Let's go back. Okay. Wacky Wednesday, dude. He's got to do his thing. So we'll let him do his thing. There we go. Wacky Wednesdays. And so with this right here, we've got a previous competition on Kaggle. And look at this R squared. 62% of the variation in what is sold in week 10. And they did the log 10 probably because it's skewed data. So we transform data when it's skewed. Is explained by all the variables. We'd be like, well, wait a minute. You know, this is a good model because look at our R squared adjusted. What is R squared adjusted? Who can tell us? 1,000 points first person. Crazy points today. You can only get up to 1,000. Or you can get 300 when I'm giving those points. Who can explain what R squared is? Give me a decent definition of what R squared adjusted is. Excuse me. Who can give me a decent definition of R squared adjusted? I want a decent definition of R squared adjusted. So that way we know exactly what that R squared adjusted is. Give you 100 points to that, Alex. We don't really interpret R squared adjusted. R squared is related to practical significance. R squared is related to practical significance. But R squared adjusted is something else. Kind of Ben, 100 points Ben right there. Henry, I'll take that. I'll take Henry's answer. R squared adjusted is our original R squared with a penalty term. There's no real interpretation of it. It's always smaller. Been adjusted for the number of predictions models. Alex, I'll take that for 1,000 right there. That's a good way. Yeah, that's the penalty term. it's adjusted for the number of predictors in the model. The penalty term is weighted by that. So we should know that R squared adjusted is our R squared adjusted by a penalty term for the amount of predictors in the model. Good correction right there. And R squared adjusted it's always smaller than R squared, except we don't play the trick circumstance. So bingo, Corbin, great job. Exactly. We're out of Red Bull now. And so we should know what the residual standard error is. 1,000 points, residual standard error. Interpret that. Give me a quick interpretation of residual standard error, which is also RMSE. Well, don't put RMSE, because that's, someone say, well, what is RMSE? Someone's like, typical error, Ryan, 1,000 points. Yep, it's typical error the model makes. When this model predicts the log 10 of sold week 26, it typically misses by about 0.4895. That's how much it usually misses by on average. I'm trying to think if there's anything else super important here. P-value is about the only other thing. P-value right here just tells us that the whole model explains more variation than the naive. Philip, 1,000 points. Yep. Yep. And then this, and then this, and then everything else. So you should know how to interpret that, and that. You should know what all those means. Square root of the mean squares, 1,000 points right there. Square root of the residual sum of squares divided by, so we won't divide it. Is it that? No, I think you're thinking about the ANOVA table, and that would be the mean sum, the MSE, which is the mean sums of error for the model. Let me think. For the mean sums, you're thinking about an ANOVA table, I believe, which will be different than the root mean squared error. No, Ben, 1,000 points. I appreciate it. That's going to be the ANOVA table. So we could get, I think we have this data inside of here. So we could look at the ANOVA for it. I like that you said that, Ben, because then you made me think. You're like, what is that mathematically? When you make Brian think, you get that 1,000 points because you tried. You made me think. That's what we want to do. No data. Wait, I gotta load the library. And there's it loaded. And so we should, what Ben was talking about, Ben is talking about, let me see, square root of the residual sum of square divided by the residual degrees of freedom. I think you're talking about this right here. That's because this is going to be, well, that's not the mean. This is it right here. Because if you're dividing by, I'll put it on the screen. This is the error in the residuals, which is 659.31, and you divide that by 2752. So this is dividing by residual degrees of freedom. So we're dividing the error in the residuals by the residual degrees of freedom, and we get that right there. So good job, Ben. Well earned 1,000 points. You made me think. I was like, if you're dividing the error in the residuals by the residual degrees of freedom, you're receiving the mean squares for the residuals. So that's the, which, you know what? It very much sounds like it, doesn't it? It very much sounds like it. Ben, you might be right. Did you look up the definition, Ben? It's the square root. Wait a minute. Ben, I think you earned a secret 2,000 points. The Red Bull hadn't kicked in fully because you said square root of that. I didn't square root it yet. Ben, you just earned a secret 2,000 points. Ben is 100% right. Great job, Ben. You didn't try. You were right. But great job. So no, look at the number because I didn't do the square root. I know. You were right. And that's why I pause on these things, because that's not the way I would say it. And then I was like, wait, I didn't square root that. And so, because wait a minute, because think what I did is wait, just look at this. Why did I not realize it? Because Ben, you're totally right. It just makes more and more sense as I read it. Because what is this called? This is the mean square. So this is the mean square right here, right? Do you see how this is the mean square? So what do we just do? If it's RMSE, what did I just do to it? You can barely see it right there. What did I do to that number to just get the number that's right there in that output? All I did to the mean square was, as Ben's thing says at the start, square root it. Ben, great job, Ben. Yeah, so don't worry. Keep trying. I mean, that's why I pause on these things. And if I'm ever like, no, I'm right, just be like, no, Brian, I think you're wrong. I don't usually calculate it that way. So I usually just look at this right here. I don't usually go to the output, divide the mean squares by the, or I don't take the sum of squares, divide it by the degrees of freedom, and then square root it. But hey, it works. That's a more classical way of doing it, but we get it in the output. So great job, Ben. Secret 2,000 points. Correcting Brian. That's what we like to see. So here's this model right here. What are the two biggest problems with this model? Go. What are the two biggest problems? You have to tell me both of them for 1,000 points. You can only get up to 1,000, but Ben has broken the rules with the 2,000. Which Ben's at 2,000 because I like it. I like when someone's like, wait a minute. Both things. Grant, I'm giving it to Grant right there. I'd say the linearity is a huge problem. The linearity is exhibited right here. There's a huge linearity problem. And then the normality I see right here. The equal spread, I'm not saying it's good, but the linearity is the first thing that jumps to me. The linearity is ridiculously bad. Linearity jumps out to me immediately. Linearity, make sure you know, is when it does not follow this line. So this has a huge linearity problem. That jumps out immediately. So the equal spread is if there's an equal spread at all points. I don't know. It's the linearity makes it ridiculous to look at that. And then right here, the normality of the residuals, that's an F. It didn't even try. We said draw down the red line. That's how you tell if it meets the normality of residuals. You say draw right on the red line. It's like, you're like, you're not trying. You're not trying to be normal. That's all right. Don't be normal, but then you don't pass our test of being normal. So you might be like, well, how can I fix this model? Well, obviously, take the ratio of sales in week 13 divided by stores in week 13 and multiply that by the stores in week 26 and then take the log 10 of that. I mean, that's obvious, right? And look, that's the only variable in the model. We just have this new variable created z right here, and then we just make a linear model of y tilde x, but the x is now the z. We're just calling it z for reasons. And then we have this new variable. And guess what? This new variable right here explains what % of the variation in week 10 sales. It's week 13. It explains, basically, what % of the variation. Last sip of Red Bull. It explains what % of the variation in week 97.88. Emil right there, 100 points. And look at the R-squared adjusted. Wow, R-squared adjusted is near perfect too. And the residual standard error is a fourth of what it was. Now, this is how you can do comparisons. You could say we typically miss by like almost a fifth, like a fourth to a fifth of what we did. I'd probably take the two of these. We still have this number right here. So I'm going to take and do this. And the residual standard error is 23% of what it was. Please note what I'm doing. I'm taking my original, I'm taking the new root mean squared error, which is my typical miss. Does everyone see that right here? My typical miss is currently this. My typical miss was that. So now we can say my typical miss is like a quarter of what it was. Like we've reduced the typical miss by 76%. Does everyone understand the mathematics I'm doing right here? I've lost my copy paste now, but I've reduced my typical miss from being basically, you can look at this, 48.95. My typical miss has dropped down to this. So just think about that. You were missing before by 0.5 basically, and now you're missing by 0.11. That's a huge reduction. You were previously explaining 62% of the variation, and now you're explaining 98% of the variation. So you've gone from explaining 62% to 98. This is how we compare models. Please take a note that the practical significance, put in the chat, first person 1,000 points, the practical significance in regression can be viewed most generally by the RMSE or the multiple R squared, which is just R squared. So we can do it, we can look at the practical significance in multiple regression or regression by looking at the RMSE or R squared. And these are the two comparison metrics I'm doing between models. You should also maybe, I mean, we don't interpret adjusted, but that'll tell you if you have too many variables in the model. Alex right there, 1,000 points. I think I give Alex 1,000 already. Mila and Alex get 1,000 because I think Alex might have 1,000 already, but both you get 1,000 right there. Great job. And so we need to know that these are practical significance measures. How do we always look at statistical significance? First person, anytime we're talking statistical, we're just talking this. Anytime we're talking statistical, we're just talking this. Anytime we're talking statistical, we're just talking this. You don't even need to think when we say, you need to think, but you don't have to think too hard when we say statistical significance. Anytime we're saying statistical significance, we're always talking this. Boom, right there, Alex and James. Yep. So James, you're at 1,002 now. We're saying p-value. Anytime we're saying statistical, it's instantaneously p-value. I can put like 5 questions on the final, like, when looking at statistical significance in a simple regression, which one of these would we look at? And I can just list off a bunch of stuff that I can just say p-value. Anytime it's statistical, it's p-value. P-value below 0.5. When looking at an ANOVA, to tell if it's statistically significant, we look at p-value. When looking at logistic regression, to tell if it's significant, we look at p-value. Statistically significant. I got to make sure and say statistically significant. Please put 5 questions. I know, right? I might. It'll differentiate between the people who know and the people who don't know, because they'll be like, ooh, I answered p-value for that last statistical significance one. I didn't pay attention during logistic. So if you don't know anything about logistic, it's still the same thing. Just p-value is statistical significance. It's always, p-values are all statistical significance. What problem looks to be fixed in this one? Now, if we do the test proper, we say, okay, look at the p-values, bad, bad, and bad. That's horribly bad. Well, and then you go here and you say, okay, we do it. Linearity was fixed. Henry, 1,000 points. You're right. Linearity was fixed pretty much. Even though we failed the linearity, it's like, it's all right. And the equal spread, I mean, it looks all right. And then right over here, the normality of residuals got problem still. This is a really good graphic for the test. I'll tell you why I like this graphic. If I say, what appears to be the biggest problem, linearity equals spread or normality of residuals, people who don't pay attention will say the biggest problem here is linearity, because they'll look at this red line and they'll say it's not following the red line, and they'll be like, oh, that's easy, it's linearity. But that red line is the normal curve and it doesn't follow the normal curve. So these 2 graphics right here are your normality, and we have here a histogram showing normality, and we have here our QQ normal quantile plot showing normality, and the points do not follow the normal curve, which is still the red line over here. This red thing over here is the normal curve. You notice it doesn't follow it completely, and that's what we're exhibiting right here. So the residuals do not show a normal pattern, and that is the biggest problem with this one. This graphic is a perfect test question because I'm not trying to trick you, but it differentiates the people who know the difference between this is just the linearity condition and this line right here down the middle is linear. Yep. It's hard to see. There you go. That red line right there, that's the red line, and then that's the red line that goes down the middle of this. Yeah. The histogram of the normality doesn't look that bad, though. Yeah, it's hard to tell, and that's why we don't look at the histogram. That's why you don't look at the histogram. I've removed the histogram sometimes. Like, I've gone into the check regression, I've deleted that part of the code so you don't get the histogram, because the histogram's deceptive. Would different degrees of freedom change the normality? Really good question right there. 100 points right there, Brad. You're at 1,000. You have some great questions today. So one of the issues with normality is the issue of power. I'm just going to mention this real briefly. The reason you might say, well, why do we fail the tests and then look at the plots? Basically, no data is normal. I mean, like, I'm sure there's some data that's normal out there, but to find normal data, one of my friends one time posted, I found the unicorn, I found the normal data. And it's like, did you? Or did you just not take enough samples? So when Brad mentions degrees of freedom are related to sample size. Sample size is related to power. The higher your power, the greater ability to reject the false null. Power is the ability to reject the false null. It means if there's results, you can find them. So don't worry, a lot of definitions here. But what I'm basically saying, let me put it in just common English so everyone can hear. If no data is normal, if data is not normal, what does having a larger sample size mean you will do to these nulls? If no data is really normal, what does a larger sample size basically mean you'll find out if you get a larger and larger samples? With larger samples, you will basically do what to the null since no data is normal? If you get larger and larger samples, since no data is normal, and you'll have the ability to find results if you get larger samples. So once again, listen to two parts of this. Since no data is normal, if you get larger and larger samples, you will eventually do what? You'll eventually do what to that null if you keep getting larger samples, since no data is really normal. It's like, no data is really normal. Like, you'll eventually reject the null. Like, that's what all these tests will eventually go to. Does that make sense? Like, since no data is really normal, like, it's like, does normal data even really exist? Well, if you get a large enough sample, you won't find normal data because you'll be like, well, it's not perfectly normal. And so if you get larger samples, i.e. larger degrees of freedom, you will eventually be able to reject the null. So these tests are designed to kind of fail. So when we fail right here, we actually go and look at the results and we say, well, how badly did we fail? Since we know that these tests will most often go towards failing, we then look at the results. Does that make sense there, Brad? That we know that the tests are designed to have us fail. So when we fail, we then look at the plots to say, how badly did we fail? Like, this says 0, so that's really bad, but is it a 0 like kind of bad or a 0 like really bad? And so we also have to look at the plots to see how badly did we fail. I mean, most often. Not always, because if we pass the test, we don't have to look at it. If we pass the test, the plots look great usually. And then you're just like, okay, we passed the test, we gotta look at the plots. The standard syntax, cool. Adding a new variable. This is just how to add it in. So the notes are in here so you can see. And polynomial models. This is one of our, got 2 less topics today. Awesome. So polynomial models. Polynomial models, just think about this. If you have a line, what's a polynomial model? Not a line. 1,000 points first person, you can put it on top of your 1,000. A line, what's a second degree polynomial model going to be? You've got a line, and what's the second degree? This is a first degree polynomial. Here's a line. What's a second degree polynomial? Second degree polynomial model would be a what model? So here's a line. I'll take quadratic right there. Is this? What is this? What am I under? I can't do it. What is this? Parabola right there, Nicholas, 1,000 points. And Mila, you get the, there we go, it's a parabola. So polynomial models are just bringing x to a polynomial power. So you can do x to the first, x to the second, x to the third, x to the fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, whatever you want. So you just raise it to the polynomial power, and they're really easy to make. So there's some views of them of x to the first or second, third, whatever you want. Crabgrave, oh man, we'll do another short Crabgrave today. And so here's the issue though. As you keep adding in these polynomial models, your r squared will always do what? As you add in more x's, your r squared will always go what? Every time you add in an x, r squared always goes this. And these are technically x's. You're just adding in like, you know, x squared, so it gets term. So you get that right there. So every time you add in an x, r squared will do what? Every time you add in an x, r squared will do what? When you add in an x, r squared must do what? Every x makes r squared do what? Go up. Go up. Every x makes r squared go up because x is explained. James, 100 points right there. So every x makes r squared go up. And what we want to do now is not compare r squared for these models. We want to compare r squared adjusted. Don't worry, you'll remember it. If you get it wrong, you remember it. That's the good thing. Is like when you said damn right there, or darn, sorry, I can't see the r's and the n's, but when you said darn right there, then so you're basically like, okay, I got it. That's you being like, when it comes time for the test, I got this. I got this. So that's what we want to see. If you get something wrong in class, totally fine. You don't want to get it wrong on the test though. You want to get it wrong in class and then be like, okay, wait a minute. R squared goes up when we add more x's. And then the way we compare models more fairly, a better way to compare them is with r squared adjusted. Because r squared adjusted is going to penalize us for putting in more x's. So r squared adjusted is the fairer way to compare models when they have additional x's in them. So here's the rule of thumb right here. This is Dr. Petrie's guideline. I think it's a pretty good one. And so r squared goes up when we add in more x variables, and r squared adjusted does not have to go up. I agree with Ben, right? Well, you got tons of points today for correcting me, which was awesome. So what we have right here, this is something Dr. Petrie has made up, but I do think is pretty useful too, is this 0.005 standard. So if you were here, I think it was 2 classes ago, we practiced this, and this is on tonight's assignment. But here's the rule, and here's how it works. Step 1. What is step 1? 1,000 points. Who can tell us step 1 for this? Step 1 is to do what with this output? What do we do? I'm going to zoom in on it a good bit here. Don't worry, I'm going to make it easier to see. What do you do with this output first for step 1? Find the largest. Emily, 1,000 points right there. We find the largest. Let's find the largest. Step 2. What is step 2? Step 1, find the largest r squared. Who can solve for the answer in step 2? Boom, nice job in the chat. Subtract 0.005. And what will that give us? What will that give us? Here, I'll do it. I'll do it. Pen's in the way. So let's go right here. Let's go 0.05. This one's going to be a close one. And subtract 0.005. Okay. Oh, that's not as close. Okay. So, who knows the answer? What model will we use 1 through 6? 1,000 points first person. So I've now figured it out. That is correct. Nicole, 1,000 points. Nicole is correct. Wow. And amazing job. Nicole wrote that all out and everything and got it right. So now step 3 is to start with the smallest model and ask, does the smallest model, we'll just use that number, does the smallest model pass this standard? Does the smallest model meet this standard, yes or no? Does the smallest model, the lowest model, meet this standard, yes or no? Does that meet? No, does not meet the standard. Does the next model right here meet this standard? When I say meet it, it means like it's above it. Does the next model meet this standard? Yep, that's when we stop. Done. And I want you to think about why we're doing this. Look at all these models. All these models here have very similar whats. Every single model right here has very similar what? Every single model right here has a very similar what? Every single from the second to the 6th degree polynomial, great job Alex right there, has very similar r-squared adjusted. So why would we use the 6th degree polynomial when the 2nd degree polynomial is very similar? Does everyone understand? Like a 6th degree polynomial looks like it's got a whole bunch of like bumps going through it. It's all crazy like, but it's like, well, the 2nd degree it does just about as good. You could say, well, isn't r-squared adjusted? Because a student said to me, and great question, they said to me, isn't r-squared adjusted already adjusted? So why are we adjusting r-squared adjusted? The reason is we like to use simpler models. And it was a good question because someone could be like, well, my standard is just to use the highest r-squared adjusted. And then they could use the 6th degree polynomial. I mean, all models are wrong. So we say in statistics, but we oftentimes like to use a simple model. We like to go by Occam's razor, which says if two things have equal explanatory power, then we should go by the simpler model, the one that makes less assumptions with equal explanatory power. So what does it mean to have equal explanatory power? R-squared adjusteds that are basically similar. But look, there's a jump from the 1st degree to the 2nd. So the line going to the 2nd has a big jump, and we should see the graphic here on the next slide. We should see the graphic, and there it is. Look at the line and see that the line kind of sticks out like a sore thumb. That's the 1st degree polynomial. But then the 2nd to the 6th are all kind of intertwined. And you'll even notice that the 5th and the 6th are kind of very, very similar. Look at how the 5th and the 6th right here have super similar r-squared adjusteds, even the 4th. So is it 4th, 5th, and 6th? Those should be pretty intertwined. Is that there's the 4th, 5th, and 6th. These are the 4th, 5th, and 6th. That's the 4th, 5th, and 6th right there. I'm not sure if we've gone over this yet, but what does the 0.005 heuristic mean? It means models within 0.005 of r-squared adjusteds are virtually identical. Ben, good question. Models within 0.005 of each other's r-squared adjusteds are basically identical. So that's step 2. 1, find your highest r-squared adjusted. Step 2, subtract 0.005 from it. And any model within that is virtually identical. Does that make sense, Ben? Like we took this, let's show it again. We take this value right here, and that's the highest r-squared adjusted. We go here, and we take that number. And there it is. We subtract 0.005. That's the 0.005 heuristic. And then this right here is our standard saying any model that is within this, that meets this, is virtually identical. So does this model right here meet that standard? Show the standard again. That model does not meet that standard, so that model is not virtually identical to it. Does this model meet this standard right here? Yes, that model meets the standard, so that model is virtually identical to it. As in, we could use the 2nd degree polynomial, or we could use the 6th degree polynomial with about equal results. So what would you choose, a 2nd degree polynomial or a 6th degree polynomial? Let me phrase it to you this way. You can have 2 friends drive you to New York, or you can have 6 friends drive you to New York. Which would you rather choose? You're gonna get to New York either way. You can have 2 friends drive you or 6 friends drive you. You're gonna choose 2, right? So just think of it that way, that we're using a simpler version of the model. We're not going to go all the way up to the 6th degree polynomial because the 2nd degree polynomial, it's the red line. The red line does just about the same as all these other higher polynomials. You might be like, well, this one has bends down here. And you're like, well, it's all about the same. Especially the 2nd and the 3rd are virtually identical. The 2nd and the 3rd are so close in what they do. There is a jump between the 2nd, 3rd to 4th, 5th, 6th, but the jump is so negligible. The real jump we see here is from the line to the 2nd degree polynomial. Does everyone see how there's a jump from what the line does to the 2nd degree polynomial? You can kind of see the bend through the data. And the 2nd degree polynomial really picks up on that. Now, there is like a 6th degree polynomial, like some sort of crazy up and down, but is it really necessary? No, it's just, you know, bendy lines are going to help more and more, but we don't really need it. So we fit the new model. We see what's going on. We get a good R-square adjusted, all that good stuff right there. And you can fit these polynomials into the model with the following code. Here is how you fit, and you need this for your assignment. This code right here, very important for your assignment. So when you put a polynomial, you do poly, the variable, and the degree to which you want the polynomial. So you can add the polynomial the following way. Make sure to look at the code, and you will get right here the polynomials in the model. Your regression equation right here, you don't have to do all this. Don't worry, unneeded. We don't do that in the assignment. So the order of the polynomial is what matters when doing descriptive analytics. We won't interpret the coefficient. So on your test, you won't interpret the coefficient, but you could say there's like a parabolic relationship between the two variables. And good, we got 30 minutes for the last huge topic. Last topic is huge. It's a big topic. So when you talk about the degree to which the polynomial relationship impacts the model, we would say something like year made has a stronger impact for later years, that it kind of levels off in the 70s or 80s. There's no constant change. There's not two bulldozers that differ in year made by 1 year are expected to differ in their price sold, their sale price by this amount. It's that when we see bulldozers in the 2000s, we see greater differences between their prices depending on their years made. Bulldozers for the 70s and 80s have smaller differences. The polynomial relationship says that the relationship gets stronger as we go further into the year 2000s. Do you see how I'm not interpreting a coefficient right here? I don't even have to look at the coefficient. I explained to somebody that in the 2000s, we see a bigger difference between sale prices of more recent bulldozers. Going back into the 70s and 80s, we see kind of a weaker relationship, which might actually say that antique bulldozers, we are basing it on very little data, sell for more money, but it kind of levels off. It kind of gets very flat. We could use, Andrew might see in his assignment, there's a spline thing or a segmented thing. You could do segmented regression. There's so many options with making models, but we could do a segmented regression right here, and this might be a flat line. But does everyone see I'm not interpreting a coefficient? I'm not saying two bulldozers that differ by 1 year made are expected to differ by this amount, because it's not a constant change. And that leads perfectly into interactions, which is a very tough topic. There's not a ton of slides on this, but this is a tough topic, so pay attention. Who's here right now? Brian's going to get that last sip of Red Bull. There's always a last sip in here. Who's here? Say yes. Who is here? That's it. Yes, Alex, Nicole, Mila, Emily. Good to see you. Brad, Megan, Corbin, Nicholas, Stevenson, Emily, Andrew, Brennan. Here but no coffee. Get some coffee, Brendan. Get some coffee. I no longer have a Keurig machine. I miss my Keurig now. I sold my Keurig because my fiance has one. And so I was like, we don't need 2 Keurigs. So I sold mine. Awesome. Okay. Let's do this. I still have a coffee. I still have a way of making coffee though. So I was like, I can still make coffee. And I'm just like, I can't just like be like, brr, brr. I mean, this is a quick aside. Like, I know Keurig is not the best coffee, but it's one of the easiest ways to make coffee. Just got an email about evaluations for professors. Oh no. Don't be mean to me, Alex. Don't be mean. That was like horrible. So let's do this right here and fill out the evaluation. I'll send out some reminders. We might try to do some sort of bonus for the evaluation. I'll try to figure out something nice. Keurig is the move. I know, and Keurig, it changed everything. Keurig massively changed the whole coffee industry. Ninja coffee makers are where it's at. Oh, Brandon, I should check that out. If our Keurig ever breaks, we might do that. Do a switch. One of my friends swears by Nespresso. Like if anyone has a Nespresso, love to hear your opinion on that. But one of my friends is like, Brian, you need Nespresso. I haven't talked to him lately, but I don't know. Maybe he's changed his opinion. Like, yeah, it's Keurig now. But he's definitely a coffee aficionado. I created more waste environmentally on here. Well, then what you should do, I see we should start doing this, is you should use the refillable Keurig cups. So Andrew swears by Nespresso too. And you should use environmental. And I mean, that'd be good because Keurigs are, with the plastic and everything, that is a bit of a problem. Good comments there, Brad. So we need to look into that. And then we need to have more biodegradable because big concerns. I do agree. Let's hop in here to the model. I guess, yeah, the only plastic I'm wasting right now is I got a huge bag of coffee and then I'm just grinding it up. And yeah, I'm using like a pour over. If anyone knows like the pour over things where you grind up your coffee, you put it in, and then you pour over it. Oh, it's good. It's good. It takes like 10 minutes to make not like 10 minutes to make coffee, but you got to boil. I don't know. You know the things to do. French press. Yeah, French press is classic. French press is good. Let the coffee bloom, getting all the sediment. Yeah, I do. At the bottom of like my coffee, I've got like pour over's legit. I totally agree. It's good. It's good, strong coffee. Gets me woken up in the afternoon. So here we are. We're going to talk about some interactions right here. So wait, here's the thing. We know what interactions are. Let's talk about interactions like in a real sense right here. Okay. So you know what interactions are. You already know what an interaction is because who here hates just straight coffee? Who here just like, man, I can't drink that straight coffee. Just like if I made you coffee, be like, no, you need to put something in that. Nicole. And then what do you want in your coffee, Nicole? Not a fan. So Alex thinks coffee is great. But what do Nicole and Brendan? Can't do straight coffee. Dennis, don't like coffee at all. Maybe don't like coffee at all. Frosted milk, creamer. So Philip needs creamer. So let's see here. Never had coffee. Wow, never had coffee. That's interesting. There you go. I don't know. Maybe try it. Maybe don't try it. Whatever you like. So Philip, what if I gave you a cup of creamer, Philip? Philip, would you like a cup of like coffee creamer? Would you like a cup of coffee creamer? Does that sound good? Like, be like, I'm just going to drink a cup of coffee creamer by itself. Not coffee with coffee creamer, but just a cup of coffee creamer. Let's see what Philip says. Philip's thinking about it. He's like, I don't know, maybe. It's interesting to see people's reactions. They'll be like, yes, totally. No, there we go. No, not liking it at all. But then Philip also said he doesn't like coffee. But wait a minute. When you put coffee plus coffee creamer, all of a sudden you get something good. Yeah, I know, right, Brennan? I know some people who do that. That's why I say that, and I do have friends like that. Brendan, 100 points for there, and Philip, 100 points. Because I do have friends who do stuff like that, like I did. I mean, they're still my friends, but they're older now. It would not shock me if Kevin still does that, though. It would not shock me. Sorry, Kevin. Shout out to Kevin right there. So, with this right here, I told him about this. Maybe he was watching today. Probably not. Two bads make a good. Exactly. Isn't that weird? Isn't that weird, Philip? That you don't like regular coffee by itself. You wouldn't drink regular creamer by itself. You put them together, and all of a sudden you get something good due to their what? Interaction. So I want us to think about this. Let's give people a taste test right here. And we're going to have what I call the bacon effect. And let's say something is rated right here with either no bacon or bacon. So does everyone see we've got no bacon and we've got bacon? Does that make sense? So let's put here a 0 and let's put here a 10. And it could be like turkey bacon if you want. So whatever it's whatever bacon, or it can be soy bacon if you don't eat any bacon at all. Whatever bacon you eat or don't eat, it works for the example. Let's go here with a burger. Could be a veggie burger if you want. So let's go here with a burger. No bacon burger. What's the rating on the no bacon burger? Okay, just going to get a no bacon burger. It's just a burger. What's the rating? I love it. Nicole, 100 points. What's the rating on the no bacon burger? A 3? Ooh, that's harsh, Andrew. A 5? I'll take a 5. Andrew's really harsh. So let's go right here. Now, let's put bacon on the burger. Let's put bacon. 4.7653. If we put bacon, what happens? This. It gets better. Now let's look at something right here where let's take, and let's go and let's take another item. Let's take a salad. What rating do you give a salad just by itself? A salad just by itself. Just a regular old salad. Any ratings for that regular old salad? It's green now. A 3. You put bacon on that salad, and what does it become? You get some bacon on that salad, some good, like, little bit of grease on the bacon. There's some grease, little grease on a little bit of bacon. I'm not saying like pure grease, but like a little bit of grease, a little crunchy bacon. You got, oh, look at that. Here we're gonna go. Ooh, wait a minute. That salad went way up. Do you see that salad went like way up? That salad went like way high with that bacon right there. How about let's take toothpaste, and let's say it's your favorite brand of toothpaste. No, we're not saying you're eating it, but we're saying it's your favorite brand of toothpaste. Like everyone's got like they like Crest or Colgate, and like on a taste of 1 to 10 or 0 to 10. Now don't say a 0 because I don't think you're like this is the absolute worst thing in the world. We talk about Olive Garden dressing salad yet. So Crest regular toothpaste. I want you to think about that toothpaste taste on a 0 to 10 scale, and I want you to give it a taste. I'm not saying you're eating it, but I want you to give it a taste 0 to 10. So I want you to give that toothpaste a taste of 0 to 10. 6.5, big fan of the toothpaste right there. 8? Man, you guys, I was going to say like, sure. Okay, we're going high on the toothpaste. I can't fight the crowd. We're going that's some really good tasting toothpaste right there. Now guess what? Andrew, I got amazing news for you. Crest came out with bacon flavored toothpaste. Crest came out with bacon flavored toothpaste. Give bacon flavored toothpaste. Oh, Alex is already saying a 1. Can you imagine brushing your teeth with bacon -9? So tell me, do you see bacon interacting the same way with, where's the interaction? The way in which adding bacon explains the taste of the product depends on the product. Everyone hear that? This is key. Let me, so let's put product right here. Listen carefully. The way in which bacon explains the taste, I'm going to erase things, I have to in order. Got to label those axes. The way in which bacon explains the taste of a product depends on what product it is. So the way in which bacon explains the taste depends on the product. The way in which adding bacon explains the taste depends on the product. Emily right there, 1,000 points. That's key. Because this right here is X1. This right here is Y. And this right here is X2. So the way in which X1 explains Y depends on X2. And that is pretty much the whole way interactions work. That X1's, the way in which X1 impacts Y is not constant. If there's a strong interaction, X1's impact on Y is not constant. X1's impact on Y depends on X2. Because when bacon's added to like food products, it's super awesome. Most of them. You can't say Jell-O. Like if you're like bacon jelly, you'd be like, I don't know about that bacon Jell-O. But when we had bacon to like bacon flavored dental floss, you're like, I don't want some bacon flavored dental floss. That's just no bacon flavored dental floss. So the way in which bacon impacts the taste of a product depends on the product, or you could say taste, because like the way in which bacon impacts how we rate taste depends on the product it's added to. That is an interaction right there. Let's see it in the, hopping over to here. Let's do it. If we have that it has the same, there's no interaction. So the coefficient of x1 is constant. The coefficient of x2 is constant. But when we see an interaction right here, we're going to see, let's look at the interaction ones. Those are just more slides. Here's where we get an interaction. If you look right here, we have an interaction between x1 and x2. Does everyone see there's an interaction term between x1 and x2? So x1 and x2 have a new coefficient right here, but if I plug in values for x1, it'll solve for an equation and we'll get a new coefficient of x2, and that's what we're going to see right here. Let's take a look at the mathematics. The mathematics works as follows. If we were to take and to plug into here values for x2, what's going to happen? So remember, b0 and b2 are just numbers. They're just weights. So b0, b2 are just weights. b1 and b2 are weights. What we would get if we solve this equation is a new line, just like we saw previously, a different line. And the math right here really shows it, because when x2 is equal to 0, we'd get this equation right here. When x2 is equal to 5, we get this equation right here, and we can solve through. I think it works better when we show the mathematics, which we show right here. Let's take a look at this. If you notice, we have a line right here when education is equal to 0. If you look, the interaction term is the following. How do you add the interaction term to the model? All you do is take the coefficient of the interaction and you multiply the two variables. But let's say we're going to plug in 0 for education. What would this become if we plug in 0 for education? If we plug in 0 for education, what does this become? First person, 1,000 points. If education right here becomes 0, like if we say if education is equal to 0, what does this term become in the model? When education is equal to 0, this would become what? That would become what? 0. Stevenson, 1,000 points, right? You're right. That would become 0. So this right here, and so it is kind of like the intercept of education, but we're saying when education is equal to 0, that's going to become 0. How about if we plug in 0 for education right here, what does this all become? Because this is 6 times this times this. If you plug in 0 for education right here, it's 6 times 0 times something else, but 6 times 0 times something else is 0. Look at what you're left with. Does everyone see what you're left with by plugging in 0? You just literally go right here and put in 0. I have to show this even better because this... I think I can put this on the test in a good way, like solve the equation, solve for the coefficient of this when this is equal to this. It's not that bad to do, but this stumps people. So what we're literally doing is we're going and we're plugging in a value for education of 0. And this would then 0 out, and then this zeroes out, and then that zeroes out, and you're literally just left with this right here. Go ahead and try to figure out who can figure out the equation for when education is equal to 1. Who can figure out the equation for when education is equal to 1? Go. 2,000 points on top of today's bonus points. Figure out the equation for when education is equal to 1. I'm going to make it, figure out the equation for when education is equal to 1. Who can do it in the background here? Who can do it? I've got it in my head, I believe. So when education is equal to 1, we'd have salary. And you just need to plug in a 1 here. And you plug in a 1 here. So the easy thing is going, it's going to be that. And yeah. Nice job, Mila. Nice job, Mila. Well earned. Yep. And then, exactly. There we go. And Ryan, Nicholas, you're all at 2,000. Great job, because I think you all kind of got it. And then make sure, Nicholas, make sure to reduce it. Make sure to reduce your equation. So if you followed along here, if you notice all we're doing is plugging in, and this would be times experience. So all you're doing is plugging in. Does everyone understand what we're doing right here? We're just plugging in the value of 1 for education and then you're just reducing. Who's like, this makes perfect sense? You're just going to plug in, you say education is equal to 1, and then you just, this is all multiplied out right here. That's all multiplied, and then you just reduce the equation. You just multiply out, reduce the equation. If you notice, these two terms will combine right here, and then this one will change the intercept. These two terms combine. Does that makes perfect sense? You just plug in the values. So that's why I was like, I think it makes more sense when you see it. You just solve the equation. That's all you do right there to solve the new equation. And we're literally doing what we did previously, because this will change the intercept and it'll change the slope. And this is what we were seeing right here, where we're going to have a different intercept. This model is a little bit different because it's categorical on the bottom, but we have like a different intercept and a different slope. And the more it changes the slope, the stronger the interaction. So, whoops, wrong button. There we go. And so we see here that the difference in the slopes is the interaction term. The slope is what's going to be the interaction term. And where did this 6 come from? How do we know it was 6? Because of this right here. Now, we did round the numbers, but this is why we chose 6. This 6 right here was chosen. Look how it's the interaction term. This is how the interaction term is stated, and this is how the interaction term is created. Does everyone see an interaction term is created from x1 times x2, and it carries model hierarchy? More on that in a moment. But it's created from x1 times x2. That is how the interaction term is created. And then all you do when you see this colon this, you go and you add it to the model and make sure to remember the minus. So we see here the two different lines. And look, when education is higher, experience has what impact? When someone has a higher education, their experience is what impact on their salary. It has what impact? When someone has a higher education, their experience would have what impact on their salary? So look at the coefficient. When someone has higher education, for those with higher education, their experience would have a what impact compared to people with less education? Less impact. I think I might have said there. Great job. So does that make sense? That given two people who have education equal to 6, we would expect the person with more experience, 1 unit more of experience, to differ in their salary by $2, the people with the high education. Now, they're expected to have higher salaries in general, but the experience plays a smaller impact when someone has more education. When people do not have any education, that's when experience is way more influential. And just think, if you don't have any education, what would impact your salary? It would be your experience. So the way in which experience impacts salary depends on education. Does everyone hear the throwback to what we did? The way in which X1 impacts Y depends on X2. The way in which X1 impacts Y depends on X2. The way in which experience impacts your salary depends on education. The way in which bacon impacts the taste of food depends on what food you put the bacon on, or the item. So for toothpaste. And so model hierarchy is our last topic of today. And what is model hierarchy? Model hierarchy says that when we have an interaction term, we have to include the components of the interaction. When we have powers, we have to include the lower order powers, even when the p-values are not significant. So how do you know if something meets model hierarchy? Meeting model hierarchy looks like the following. If you're doing a two-way interaction, and you have x1 and x2, what needs to be in your model to build up the tower this high? If you have x1, x2 interaction in your model, what needs to be in your model to keep model hierarchy? To keep model hierarchy, what would you need in your model if you have x1 and x2 to preserve model hierarchy? Which we don't have to. It's kind of nice to do it, but what would you need in your model to preserve model hierarchy if you have the interaction between x1 and x2? So when there's an interaction term, x1 and x2. Yep, Brad, you got it. Brad, you're at 2000. You've answered a ton today. It's awesome. x1 and x2, keeping them in the model preserves model hierarchy. And we saw this in the notes previously. This model here preserves model hierarchy. This would be an easy question. Does this model preserve model hierarchy? Yes, it does, because there's an interaction term, and then we have the lower order terms. If you were to remove one of these terms from the model, it would not preserve model hierarchy. Does that make sense? Because there's the interaction term, x1 and x2, it's just experience education, And then we have education experience that preserves model hierarchy. And we see that right here. There's the interaction and the other ones are in the model. Now, when you have polynomial terms, if you have something to like the third degree polynomial, how would you preserve model hierarchy if you have like x sub I? Don't worry about the sub I. It just means like your second x is raised to the third power. So whatever x in the model is raised to a certain power, like the third, what would you need to have? So if the I is confusing, it just means like a certain x. We can just call it x to the third. So if you have an x raised to the third power, what would you need to preserve model hierarchy with this one right here? What would you need to preserve model hierarchy? If there's an x to the third power, yep, Mila, great job today. Excellent work. Yep, you need this. Do you see how it's like a tower you're building up? That if you're going to build your tower up to this right here, to preserve model hierarchy, you need the following things. So if you have an x to the third degree polynomial, you need x to the second and x to obtain kind of that third degree polynomial. Now, you don't have to do these things. You don't have to preserve model hierarchy. It just is a kind of good idea. It's kind of a nice thing to do. We're like, hey, you preserve model hierarchy. Good for you. You don't have to do it. You can see right here that this one's missing the second degree polynomial. So if you look right here, we have first degree polynomial, third degree polynomial, no second. You can see right here, we have x2 and x3 interacting, but we have no x2, x3. These all preserve model hierarchy. So you can look to these key examples that we don't have the things that build the interaction here. We also don't have the lower order polynomials here, which are required to meet model hierarchy. Interaction plots, this is just a visualization of what we've been talking about. And remember, I wish this was actually earlier, but remember how we said the way in which experience impacts salary, or the way in which education, you might say, wait, that says experience. That says education. The way in which education impacts somebody's salary depends on their experience. This goes way back. The way in which education impacts salary depends on experience. And people who have large amounts of experience, their education would be to do what to it? People with very large amounts of experience, for people with very large amounts of experience, their education would probably do what to their salary? For people with tons of experience, it does what to their salary? Virtually what? For people with tons of experience, large experience, when someone has lots of experience, it'll do what to their salary? Their education would do what? For people with very large experience, virtually nothing. It's like it just doesn't do anything. If you have a ton of experience, then your education does not really impact your salary. But for people with very small experience, see it's the blue line? With people for very small experience, what does education do if you have very little experience to your salary? If you have very little experience, education now has a very positive coefficient. Does everyone see the way in which education impacts your salary depends on your experience? For people with very little experience, education is extremely significant and has a very high coefficient. For people with very large experience, education plays virtually no impact, and we wouldn't really see changes in people's salary who have very large experience based on their education. We don't see many differences in salary, monthly salaries, based on people with very large experience who differ in their education. So you can write out the implicit lines right here, which we practiced earlier, but the big thing about interactions right here is that when we have an interaction, I can't repeat this enough, the way in which x1 explains y depends on x2. Graphically, will there be a single convergent point on the plot? Yeah, so the single convergent point, I figured it out a few semesters ago, like why it's here. And actually, yes, the naive model. This is the mean of y. All models will hit this convergent point. So this is actually the mean of y because the naive model would have to go through there. I was like, I remember some theory on why it goes through there. And why does every model go through the same point? I mean, the naive has to go through the mean of y because it is the mean of y. And why does it go through at the same point? Is this the mean of education? Surely not. That can't be the mean of education. Is The mean of education is 6. But why does it all hit? Like every model could have a point. Like this model could go up and go right there. It's like every model goes through the mean of y. And that's the naive model. That's the end of class. And theoretically, why must every model do that? That's the salary data set, right? Because if every point has to go through there, then that's the mean of y. So data salary. And then if we go to mean of salary, $ salary, we should get 3760 or something. Ooh, wait, that looks different than what I thought it'd be. There go. Is that accurate? This is the salary. Let me run this right here. Let me run this plot. We don't have the model yet. I guess you could just set each polynomial equal to each other and solve for y, right? Isn't that the same thing? Well, these are interaction plots right here, and the interactions are being weird. There we go. Trying to think through the theory on this right now. And it is actually not going through the mean because I thought it would. So yeah, I got to think through the theory on this real quick, or I got to be thinking about it and why theoretically they all go through the same point. It's a tough question. Like theory stuff can be really tricky. But I was wrong about this. Wouldn't be the median. Yeah, I mean, it wouldn't make any sense. But wouldn't... I wonder if it's related to convergence point. It kind of sounds like that, right? I wonder if... See where exactly... See what we could do. Well, I don't get... Let me see if we can ab line to it. What happens if I go AB line? AB line... You know what we could try? Let me try this. I'm going to try something weird right here. Let's try this. I've never tried doing this to this plot. Cool. That doesn't look that good, but it added it over there to the plot too because this makes a plot window. And so it appended it to that plot. And that one's off the chart. So we can't see that one. That's not... Because... No, I was wondering what you were saying, Andrew. That one right there. So that's not a good graphic, though. I'll have to think on this. I think one semester I figured it out why they all... Oh, wait. I think I'm remembering now. I think my brain's booting up. Let me look at the summary. That should give us more clues. Summary should give us more clues. So, let me look at the summary of this. Okay. Why can't I think? We figured it out one semester. I don't think it's the mean. If experience did something to the line, it would slope up. Well, so experience, the coefficient right here, experience makes the line, as experience goes up, then the coefficient of education goes down. Do you see right here? This is a kind of good final review. As experience goes up, the coefficient of education will go down. As education goes up, the coefficient of experience will go down. And you can see it over here in these graphics. Here we can visualize it, make it look normal again. But you can see these are larger educations right here. Like education going up, the coefficient of experience is going down. Experience going up, the coefficient of education goes down. So the interaction right here makes it so that we see smaller coefficients of experience or education, depending on if there's higher experience or education. So that's the easy part of it. The theory part of it, it just keeps stumping me right here, why it has that point right there that they all meet at. I mean, two lines will intersect at a point if they're not parallel, but why do the 3 points intersect at that line? And there's something about that point right there. And I can't remember what it is. There's like a theoretical reason. It's just theory. Theory's fun, and it's like stumping me again. I just want to remember it. I feel like it was Nick Brown who he and I figured it out. We're like, okay, wait a minute, this. Wait a minute, this, and we were like, oh, that's why. So I'm putting a bounty on that 5,000 points. If anyone can explain theoretically why the points converge at one point. So the theoretical convergence, because that's one thing that jumped out of my head right here, is I can't remember why there is that convergence to one point. And it's not the mean of y. We confirmed that by looking at the picture, because that is nowhere near 3,600. Maybe I just thought it was. But that means the naive model would not intersect there. Let me just look at the naive model. Because, am I going mad? Whoops. Oh, I did not run this? I am going mad. Oh, dot. Oh my gosh. I'm going mad. Yeah, that's not the mean. And so the naive model... Wait. Okay, now I'm starting to think I know something. Let me look at... But no, this... 32... But this is without the interaction. If they don't meet at a point, there wouldn't be interaction, right? Yep. Well, and so the weaker, so Jordan, great answer right there. The weaker the interaction, the more parallel the lines. So, which I should mention, but Jordan, that's exactly the thing, is when the interactions are weaker, the plots will be more parallel, which is a really good thing to know. So the more perpendicular the lines are, the stronger the interaction. That's perfect theory right there. So we go here to visualize model, and I'm trying to make a weak interaction. So this interaction right here is actually statistically significant. So let's find something that's not. It's hard to find things. I mean, sorry, it's not statistically significant, but it's lower than I'd like it to be. Text per day. That's probably going to be significant too, or close to. Okay, this is not significant at all. This is way. So these lines will be more perpendicular here. And if you look at, they do intersect, but if you look at how perpendicular they are, like they can't be perpendicular because they're not, they do intersect at some spot. But if you look at like how much they follow each other, there's not a strong difference between the slopes. Does that make sense, Jordan? That we don't see a big difference between the slopes, and the difference is not statistically significant. Like, how do you know if an interaction is statistically significant? P-value. And then if we were to look at something like desired weight, I think this will be not statistical. Wait, it is statistically significant, is it? Yeah, well, wow, that's statistically significant. So even though these differences here are small, they do look small too. There is a statistically significant interaction. Now, we put in the notes, obviously, a way stronger one, so that's why we often put in the notes a really good interaction, or it just looks stronger. Depends on sample size, depends on standard errors. But if you look right here, you see more perpendicular nature to these lines. So the more perpendicular they are visually, generally the stronger the interaction. You might say, wait, Brian, this plot and these plots look kind of similar, but it's just, look at the p-value to know 100%, because the p-value for this one is this, and the p-value for this one is this. Yes, the more perpendicular the lines are, the stronger the interaction. The more perpendicular the lines are, the weaker the interaction. Oh my gosh, perpendicular does mean this. The more perpendicular the lines are, the stronger the interaction. I should just go on autopilot and say the first thing I'm thinking. The more perpendicular the lines are, the stronger the interaction. The more parallel the lines are, the weaker. So if you're still here from 320, sorry, my brain just kind of got scattered there. But the more perpendicular the lines are, the stronger the interaction. The more parallel the lines are, the weaker the interaction. The way to know if the interaction is statistically significant, first person 1,000 points, I'm going to take a quick break, is to look at the what. The way to know if it's statistically significant, to see if it actually matters and actually helps us, is to look at that what. To look at that, to know if it's statistically significant, look at the... Someone knows in chat. P-value, Stevenson, 1,000 points. Great job right there. Let's take a break. Hey everybody, how are we doing today? Good morning. So Ryan, Thursday is bingo night. Is it bingo night? Is that's what's happening? It's good to see everybody. How's everyone doing? Hey Jenning, how you doing? So we got everything going on right here. We got the notes going up. Hey, good to see you there, Sean. So good to see everybody. We'll get started right here. Let me hop in. I'm going to load up some new notes. We were talking about interactions right here in 320. So if you're looking for a decent review, things like 320, we go through, we review, and you can watch the class. You can check it out. Reviewing, we're logging in. We have a lot of assignments coming up. But how is everyone's morning going here? How is everybody? That's all right. I was like, huh, you know, we good. And I should have mentioned this to the first class. The grader is catching up. So the grader is catching up on everything. So thank you very much to our grader, who's going to be catching up on all the grades. They had a good Father's Day weekend. So they're married, they've got kids, and they do a bunch of things. And they emailed me last night. I didn't answer your question. Oh, what was the question? And you'd like me to come. That's so I told you I don't go anywhere. I'm so sorry, Andrew. I'm so sorry. I don't go anywhere. I avoid everything at full cost. I'm so sorry. I'm a super scaredy cat with the current world situation. Oh, and then okay, we got the labs. But yeah, I'm like a scaredy cat, and I hang out indoors at all points and never leave. Well, I go on walks. I'm so sorry. That's awesome though. Hey, what's up, Sarah? I'm so sorry. No, I know. I've had a bunch of people like asking me like, "Hey Brian, you should go do this or go out, do this." And I'm like, "I don't go anywhere. I don't do anything. I don't get my hair cut." Yeah, no, we already had the notes downloaded from yesterday. But yeah, it's to talk about the current world situation. Does anyone seen the most recent numbers? Who's seen the most recent numbers from sorry, like sad topic start the day. Let me pull up the chart to show you. 7-day moving average. There we go right here. So I think yesterday was the third highest day ever. And so here is and you have to look at the 7-day moving average on it. And so here is what we have going on, and that was yesterday. And so, I don't know. It's one of those crazy things. Oh, you did? Oh, Connor. I was like, what? So yeah. So it's, but this is what we do in statistics. So I'm always obsessed with these numbers and looking at these numbers and seeing what's going on. So this is what we do is we analyze data. And here's the thing though, is if we go back 7 days, I think the 7-day is right here. So if I'm guessing what's going to happen, we're going to see this. Probably. So go back and look at this data, but this week is probably going to hit the peaks we have here. And we're going to go back down. I don't know what's going to happen, but if you were to put this trend out further, it's going to trend like that. That's the 7-day trend. But does that make sense to everybody? Like, this is what we do with statistics. You're to involve your 320 studies. But we'll see what happens because, when you extrapolate from data, you don't know where it's going to go. Like in this point, it was flat and you can't be like, oh, it's going up. Like it could go back down. Who knows? But, this is the most, it's got like a logarithmic curve right here. And then we see it leveling out. And that's what we do. We just analyze data. That's what we do. We do know, let me show you the 3-day pattern. There's a kind of a bendy curve through the 3-day pattern. And so you can see, and that's what I'm kind of showing, right? If you look at the graphic I have on screen now, I kind of know what the 3-day pattern generally looks like for this, that we see this kind of up, down, up, down, up, down bend through the data. And these are smoothing or moving averages. And this is the kind of stuff we need to know for data because, yeah, we'll see what happens. I know it's like, the reason I'm mentioning this, it's like, I know it's a kind of anxiety-driven topic. Hopefully I'm not. Yeah, and this is what we do. We analyze data. And here's the really good news, though. I don't know. One of the guys I watch on YouTube analyzes the mortality rate, and the mortality rate's gone way down. So the good news is mortality rate's way down. This is like the one, like, yay, mortality rate's very low. We see this a lot in the deaths, but the deaths have like a 14-day lag. So if you trace back where the peak is on this graphic right here on the new cases, you see it peaks on like April. The first peak right here, the first big peak is on the end of March. And then if you go and you look at the other graphic right here and you look at the lag on it for mortality, you're going to see the first big peak, and it's debatable, like, which is the first big peak, because there's two peaks. So it's like, okay, what is the lag on this? Because there has to be a lag. Like you don't get COVID and die. So the lag on this, depending on where you say the peak is, like we could debate about it. It's either going to be here, here, or here. And so what I would do is I'd probably say it's about here. Like where's the peak really at? So if you look at that, there's like a 2-week lag about. So there's a 2-week lag where we saw the peak in the first graphic was here. So this right here was the peak in the first graphic, which is nowhere near the peak on the mortality. So when you're looking at what's happening in mortality, you have to go out probably about a 2-week window to say the cases and what happens. But we are getting better treatments for severe cases and stuff like that. But this is how we analyze data. And, I do bring up these topics because this is very important. This is what we do in this class. Remember, this line right here represents where we saw the peak for the previous graphic. So the previous graphic had a peak here, and then going out, depending on where you say the peak is, you've kind of got about a 1 to 3 window reach, and you do see kind of this 7-day lag pattern. But this is what we do. This is data. I know it's like not the funnest topic in the world, but better understanding data. And we are seeing that is higher. That is, I think it's this day. I think I looked and it was like 829 to 835 or something. I think, yeah, because it's like 800. So I look at this data every day and so that's, that's why Brian is crazy. So Brian has gone mad. Brian's hair's, you're going to see me a year from now. My hair's going to be all the way to here. So one of the YouTubers I watch, Brutal Moose. Does anyone know who Brutal Moose is? He's got like really long hair. I don't think I could ever get my hair that long, but it looks pretty crazy. I mean, like crazy in a good way. It's like, whoa, because no one probably knows who I'm talking about. He's a classic gamer type guy, but yeah, his hair is like, I'm like, how do you do that? I couldn't handle it. Right now, my hair is getting long enough that I'm like, okay, I'm ready to be medium hair Brian again. With that, how's everyone doing this morning? With that short talk, shave it. Oh no, that's the one thing I never. No, I always gotta have some sort of floopy hair. So buzz it live on stream. You guys are also with this session. Just got Starbucks. That's awesome. Starbucks had like a 20% off, and I was like, I really want some Starbucks. So I want normality of life again. Man, I'd like some Starbucks. What are people's favorite drink at Starbucks? Like, if you can get one thing at Starbucks, what would it be? What's that one thing you would get? This is how we collect data. See, then we could put it into subgroups. What is the one thing you would get at Starbucks? The one thing you would get. And we're going to talk more about logistic regression coming up right here. Cinnamon Dulce Latte. That sounds good. That sounds excellent. Starbucks Nitro Cold Brew brings you back to life. Yeah, Nitro Cold Brew. That's like, the Nitro, like, I can't remember what that is. Nitro Cold Brew. I should try that. I know my fiance likes cold brew, so I should get her like a Nitro Cold Brew, iced matcha. That's like matcha tea. Is that matcha tea? Is that what that is? So Dunkin', you're in the Dunkin' group. I like the Starbucks Double Energy, Starbucks iced in a can. Yeah, I do like those. I do get those. Get a lot of canned Starbucks. So we got a lot of people fan with the matcha right there. Frap. Got to go with those frappuccinos. So here's Brian's last quick story. There was a place at Appalachian State called Tradewinds, I think it was, which I think we actually had one in Knoxville here down by Best Buy. But it was Tradewinds Coffee Shop. And they had a like Frappuccino type drink. And this is like 2000. So I didn't really know about Starbucks then. I mean, I like this better. But they would take and they would blend together a coffee drink with chocolate covered coffee beans. So they would take the chocolate covered coffee beans and they would blend that in. And I should try this. I should try to recreate it. I wish I could just find someone who worked there and be like, tell me the recipe. Because whatever that was, I would get that drink and it was like the best drink ever. Like I remember the first few sips of it, I was like, oh my gosh, this is the best drink. It's kind of like a bubble tea. Boba tea. I can't even talk today. But like when we first get like a really good bubble tea and that iced coffee drink, oh man, not together. Don't drink those together. But bubble tea is amazing. For those who haven't had bubble tea yet, try some bubble tea. We get like, yeah, boba, some boba tea. So and also like Thai tea, boba tea, all that good stuff. Try everything. always experience the world around you. It'll make the world a much smaller place by going out and trying all these things. It's rare that I've had something I don't like from like a different area where I'm like, let me try this, and then I mean, I've had things I don't like. And who knows? Kind of sometimes it's what you've grown up with. And you try it more, and you're like, okay, I like it. Olives, don't like olives. I know the person who makes the cheesecake at Cheesecake Factory, and I've asked him for the recipe so many times. Yeah, I'm sure he's under contract, so say no. I'm allergic to tea and leaves. No, oh, I'm sorry, Hannah. One last quick story. I know I keep saying that. I had a student who was allergic to like everything. He was allergic to, I mean, I'm sure he probably still is. He was allergic to like milk and wheat. He's like gluten, everything. He's like, yeah, he's like, my mom, whenever I went anywhere, I would have to bring all my food with me. And he's like, I've just gotten used to it. I don't know what ice cream tastes like. I don't know what pizza tastes like. But, and he was so positive about it. But, I think I might have brought something. I might have brought candy, and he's like, I can't have any. I was like, no, it is. You're one. And he's like, no, I'm allergic to everything. I was like, oh, you're allergic to like M&Ms? And he's like, I was like, well, there's no peanuts in these. He's like, I'm allergic to milk, gluten and lactose. Yeah. So, and that's the thing is, and I just, it was interesting asking him. Yeah, he actually was like super like healthy and fit, because he was just like, yeah, I've got like this, and this, and this, and this that I eat. So he was actually like really on top of it. And I guess if your diet is that restricted, you kind of like focus in on the things. So, he definitely made the best of it. All he did is salads and chicken. You see, you figure it out, you make it work. And so I just can't see no major. Yeah. And so Andrew and I are in the same boat. Andrew and I are blind buddies. I had 2 surgeries at 2 and 12. Well, not 2. I had a surgery at 2 and I had surgery at 12 on my eyes. So I've had 2 eye surgeries in my life. Enough about me, more about you. We talked about COVID. We talked about the world. Let's start talking about logistic regression. When it comes to logistic regression, we instantaneously need to know this. Whenever you hear logistic, and 320 will be going over this, so if you want, hop into their class tomorrow. They're going to get a much more in-depth view on the basics of logistic. Whenever we do logistic, we're doing a prediction on what? And here's some hints right here. These are all hints on what we're predicting with logistic, because you should look over all these, and we'll talk about all these real briefly here. Kappa, no one cares about kappa. We're predicting probabilities, we're predicting a categorical, we're predicting the percent of something being likely to be something. Instantaneously, you should know things like that. 100 points, all those answers, up to 500 points today. I might give out some secret thousands. We're predicting the probability of something being something. Like, what's the probability someone makes a purchase? What's the probability that somebody needs an eye surgery? What's the probability that somebody has a disease? These are all logistic models. And you think about this, really, like the false positive rate, the false negative rate. I know we're talking a lot about today's world's events, but what does it mean to have a false positive for a disease? What does it mean when something has a false positive for a disease? What does that mean if you say to somebody, I had a false positive, which you wouldn't know it till you find out you don't? Like, you would be told something, and then later on you'd be like, oh, that was a false positive. Yeah, positive result but incorrect. Ishan right there, 100 points. That you don't actually have the disease but tested positive for it. Yep, exactly. Toss and Andrew. So a false positive, and so it doesn't always have to be for a disease. A lot of times I like to talk about in this chapter, my sister who's in real estate, she, does house sales in Knoxville. And so when you look at if she's trying to market to people, what does a false positive mean for her? Well, false positive would be, she would say, I should market to this person and like try to acquire the sale and try to work with them, but then they don't actually turn out to be a sale. So she might like have a model saying, here's the people I should reach out to. And then if she has a false positive, the person who's a false positive is somebody she would invest time in who doesn't become a sale. A false negative would be somebody she does not invest time in who would have become a sale. So which of these costs my sister more, maybe? The false positive or the false negative? So once again, here what these are. The false positive would be somebody she invests time in who does not become a sale. And the false negative would be somebody she does not invest time in who would have been a sale. Like she's saying, like, no, I don't think there's an... And you might think it'd be the false positive. I think it actually would be the false negative that would cost her more. It's a lost opportunity. Everyone's saying false positive, but think about this. You'd have to think, how many hours would she spend working with the false positive? And I bet there's a lot of false positives, because she probably works with a lot of clients who end up not buying. I should ask her, but she'd be like, how many clients do you have like a month, and how many end up buying houses? And if she would be like, oh, I have like 100 clients and like 10 end up buying a house, which those numbers are probably way different, then there'd be like 90 false positives, which you would get this because you need to kind of, you know, not everyone's going to buy a house. You'd have people who are like, oh, well, we're, I don't know. I don't know how this works. I know she is so like, she's super high energy on this stuff and she works super hard at it. Yeah, she's really good at it. She's really good at it. I don't know how many she has a month, but she is one of the most organized people there probably is, because she has all of her records. She has everything. And I think she's still running. She has an Airbnb. And before the world went crazy, you know, her Airbnb has like a super host and all those things. And she's like one of those Airbnb people that has like the snacks in the refrigerator. And, you know, like it's like really nice. It's got TV. But so isn't it like an opportunity cost? Yeah. Yeah. That's her false negatives or opportunity costs. Jordan, 100 points right there. Her false negatives would be opportunity cost, because if she has a false negative, she probably loses like, you get like, I don't know, like 2-3% on a sale. So if she sells a $200,000 house, she's going to lose like $4,000 or $5,000. So if she loses $4,000 or $5,000 by not meeting with this person, and maybe it's like a 20-hour investment, well, 20 hours, $2,000, that's $100 an hour. So she loses $100 an hour by not meeting with that person. I don't know what the time investments are. I could be way off. She'd be like, Brian, I work 100 hours on each client. So she has an opportunity cost for every client she does not receive a sale with. But a false positive right here, she's going to lose the time. So this is one of the hardest things right here, is this equation right here between how do we balance our false positives and false negatives? Like, what way could she, if she had infinite time, what way could she get every sale? She could just work with every client. What way could she avoid getting no false positives? She could just like quit. So she could then just be like, I'm not going to take any more clients. And then she would have no false positives, because she would never say that someone's going to have a sale when they won't. So you have to find this balance, and you have to look at the cost between the false positives and false negatives. So it's a very, very tough equation, and all this right here. So that's what false positives, false negatives are, and how often we have our false positives, how often we have false negatives, our false positives, false negatives rate. Misclassification is just the overall error she would make, like how often she how accurately or inaccurately misclassification, and it's just the complement of accuracy. So these two right here are just complements of each other. You will either classify something correctly or incorrectly. AUC, let's go ahead and talk about AUC. That's a huge portion of today's lecture. Let's jump into AUC. Let's do it. Okay. So I've already brought up my sister working in real estate, and that's why it's so important to understand what AUC is. So if you think about a model where it accurately predicts 80% of the time, oh yes, Sarah, great question. 100 points, Sarah. RMSE is for what? RMSE is for what kind of data? RMSE is the typical miss the model makes, and it's for what kind of data? You have to know this instantaneously. This is on the final. I've already got some of the final written. RMSE is for what kind of data? This is something you need to know, like that. Quantitative. Ahmed right there, 100 points. Quantitative. You have to know RMSE is for quantitative data. So RMSE is for quantitative data, and then you have to know that misclassification is for categorical. So we'll never use RMSE for categorical for predicting in logistic. RMSE is not for categorical. The misclassification is for logistic. So huge difference right there. Whenever we're doing RMSE, it has to be quantitative. We're predicting like how tall someone is, what's their GPA, how many hours a week they study, how much they spend on food a month. Whenever we're predicting things like, will we make a sale? Does someone have a disease? Is the email junk? These are all yes, no probability questions. And these would all be, we would use either accuracy, misclassification, or ROC, AUC. So and hopefully that makes sense. ROC, AUC, misclassification, accuracy are all for categorical. And these are, I can just throw these on the test. And these are key things we should know whenever we're making models, is like, how are we going to gauge how well the model does? And yep, great question, Sarah. Sarah, 1,000 points. Thank you for asking that. It's one of those things you should know really quickly, and that's why we practice it. Please ask the questions when you don't know them. Please, I'm not saying like, oh, you should know this. I'm saying now you know it. What is ROC? Great question. Nishan right there, 1,000 points. I love when you guys are asking this. Guys and gals, everybody asking it, because we need to know what is ROC. ROC stands for area. Wait, that's not an R. Area under the receiver operator curve. If I knew how to spell receiver. I before E, except after C. Ooh, it's sounding like neighborhood way. I should say, see, there we go. ROC stands for area under the receiver operator curve. We got spell check now. We don't need to memorize stuff like how to spell. It does it for us. So ROC stands for, and that's why we sometimes call it AUC. So you can sometimes hear it called AUC. So you'll see it called AUC also. So ROC and AUC are the same thing. I can't state that enough. That ROC, AUC is ROC. It's just statisticians like to call it by either AUC or ROC. ROC is the name of the curve itself. So let's just draw what it looks like. This is the ROC curve. The ROC curve looks usually something like this right here. Here's the ROC curve. That green line right there is the ROC curve. And then the AUC is this, because the AUC is the what? No, we should do the following. Let's make it clear with the colors. So here's the ROC. That's the ROC. And then the AUC highlighter. The AUC is this. That's the AUC. It's making green. Don't make green. That's the AUC. So this is now color-coded for you to see what is what. So the AUC is the area under the receiver operator curve. So I've got it color-coded right now. Do remember that this is kind of sharing a dual relationship between the two of these. That this is the C in the ROC, and this is the C in the AUC. So hopefully, does that make more sense? Yeah, they're the people just use them interchangeably to mean the same thing. Like they are different things. Does that they're different things? They are like ROC is the curve. Like the ROC is that curve. That is the ROC curve, and then the AUC is a mathematical measure of the area under it. So the AUC is the calculation we care about. But people sometimes say it's just ROC. Like, sorry that people use it interchangeably. And if you think, what is the maximum ROC can be? What is the highest ROC can be? So good I didn't block it. What is the highest ROC can be? People, while they, once again, to go, Joss, great job, 100 points right there, you're right. It can be 1 because it's a 1-by-1 block. And we'll show how to calculate it here in a second and what it actually means. It's your false positive, false negative, and my brain is working at 100% right now, so I can do some examples with it. We'll look at just how to calculate it. So we have here that the maximum ROC, or AUC, is 1, which is the area under the receiver operator curve. And so this is a huge important thing right here, because you're like, well, what's the whole point of this? Why would we use this? It's your false positive to your true positive. So it's your false positive to true positive kind of ratio. And if we were to just randomly go through our data, what would we kind of expect? We have down here at the bottom, and that's we have here the true positive, and we have here the false positive. I'm just thinking through. Wait, no, that's true negatives, right? It's true negatives. Let me just think. The bottom axis I've gotten flipped before. Let me think here. The bottom axis, you know what I might even do? I'm going to cheat, because you can always cheat. I'm thinking through the theory, and my brain is just like, I need one more Red Bull to get my brain 100% again. I need one more Red Bull. ROC curve. Someone's going to put at the bottom. It's false positive, right? It's true positive, false positive. There it is. Okay. I knew something was wrong. I was like, brain is not working. So it's true positive, false positive. Okay, cool. Thinking through this. I think the way they have theirs labeled, everyone's putting false positive, right? Yeah. See all the... Yep. Okay. Is random chance. Exactly. This is the random chance model right here. This black line, which Toss points out, This is the random chance model right here. Kind of, we were just randomly guessing if things were if it was an actual or not an actual, yes or no. That's the random chance model right there. And we kind of want to do, we would expect our model to do better than the random chance model, because if you're just going to guess if something's right or wrong, you'd get it right 50-50 amount of the time right here. And so when we go through right here, and let's take a look at this graphic. I was drawing it out literally just like a month ago. And let's take a look. So what we have right here is some data. Let's go ahead and take this data and see what we have. So this is making sales. And we're going to take this data right here. And let's go and put some data here. So are we ever wrong more often than random chance? I think it can happen. At least on the training data, you wouldn't be, because the model will not give you coefficients. The model won't do worse than the naive, but it could on new data. The model could do worse than it would be by random chance, but the way the coefficients are found, your model can't do worse than the naive. Like, it can't do worse than random chance guessing, because the model will make coefficients. It would, if the variables are so bad, the model won't add in the coefficients. Does that make sense? So the lowest, what ROC, or AUC, excuse me, what AUC is kind of the worst we can do? What is like the worst AUC you can generally get? Like, what's that's a horrible AUC. Like, what is a really bad AUC? A good question right here. This is, you could, if this was a numeric entry, it's pretty easy. No one said it yet. Hint, this is the answer right here. What's a really bad AUC? That's the answer right there. 0.5. Yep. 0.5. The 45-degree line, and that makes it 0.5. So, and we shouldn't get less than 0.5. 0.5 is just like the worst we can do. This is like the random chance model, the green line is, and that's kind of the worst. So the best we can do, like a super awesome AUC, the absolute best we can do, and you'll kind of see what this means, and we'll show it in the model, but the absolute best we can do is if we have this. And then the area under the curve, which we have that as the, would be 1. Does that make sense that the area under the curve here would be 1? And what does this mean? I went through all my true positives before going through any false positives. So we can look at our true positives here and our false positives and how quickly we go through them and what the area under the curve would be. And we should see this if we have false positives or true positives. And it should work out. You'll see it mathematically here, and we'll calculate the true positive, false positive rate. And we'll look at this here, and this is a good review of the topics. The worst we could do by random chance, we would expect, is kind of this, because you would kind of get a 50-50. How's the area 1 again? It's a 1-by-1 block. So since it's a 1-by-1 block, it makes a, no, good question, because it's a 1-by-1 block. And so there's, and then if you cut it in half, then that's half of a 1-by-1 block. So the worst we can do is 50% for AUC. Does that make sense right there? Like, it's a 1-by-1 block. So if you have the total area underneath it is 100% and half the area would be 50%. Does that make sense why AUC? So it's area under this curve, and the absolute best the curve can do is the curve could go immediately up. So the absolute best curve is a curve that goes like whoop, whoop, like that. That's an awesome curve. And we can make this, no, good questions. This is, it's a complicated topic, and it's very useful. We're about to see how useful it is. So my sister is trying to predict right here, not with space pen. We have the black pen clicked. Why does space pen? So we have right here, the probability someone will make a purchase. We have right here truth. Let's go prediction first. So we're going to make a prediction, and we're going to have here truth. Okay. So my sister says, Brian, I need a mathematical model. Let's do 6 points. That'll be easy enough. Okay. She says, Brian, I need a mathematical model that's going to predict if someone's going to make a purchase. So someone go ahead and tell me the first probability that it predicts. We're going to predict if somebody will make a purchase, the level of interest is last. So level of interest is last. So we're going to predict yes. This is important for today's lecture too. The level of interest is last. So we're going to predict yes as the level of interest. So whatever the probability is, since the level of interest is last, we're going to pick yes. So we're going to predict 50%. What R actually does then is it flips a coin. So if it's 50%, R actually uses randomness to not use all 50% as yes. Some models will, and it is in the notes, some models with 50% will predict the level of interest. But a lot of the algorithms in R will flip a coin because it's not fair for 50% to always be yes. So some models will use randomness to flip a coin. And so we actually had to, in some of the assignments, we've actually had to set the randomness because if you get a 50% probability, yeah, R's got tons of coins. It's always flipping coins. Tosh right there, 100 points, cracking me up. And Vajrana, and then 100 points, and Madeline, 100 points too. So give me a probability other than 50% because that's not a fun one. Well, give me a probability. I don't want to do 50% because then R is going to flip a coin in the background that we really don't see. 25%. Awesome. So what would the model predict? What would the model predict if the probability is 25%, 70%? 0.4. Any others? Here we'll do, we'll put them in order. We'll put these in order right here. So let's go right here. We had, well, you guys are low on the probabilities. You guys don't want to make sales. Here, we'll do this. We'll take some of these probabilities here. Like 98%, 90%, 70%, 48%, 10%, and 1% right there. So now we would predict this person would be a yes. This person would be a yes. This person would be a yes. This person would be a no, no, and no. Does everyone see how I'm making these predictions right here? This is in the notes, but does it make sense that if something has 50% or above, we predict the level of interest? If something has lower than 50%, we do not predict the level of interest. Now, R will flip a coin for exactly 50%. We don't have to worry about that. It'll do it for us. So you said 50% or above, Brian. Well, that's what we do when we assign it. So if we were assigning it by hand, or I guess you could pull the coin, flip it if you really want. But R will do a randomness procedure to split up the 50-50s, that where it's like, but does this make sense what I've done right here in assigning the prediction? So I've got the probability, which the model gives, and then I have the prediction that we're making from the probability. Does that make sense, how I made these predictions right here? That's a key thing you should know, is how the model in Logistic makes predictions. It assigns it based on the probability. For probabilities greater than 50%, we predict the level of interest. For probabilities less 50% or greater, and for probabilities less than 50%, we predict not the level of interest. Level of interest is the last alphabetical. So level of interest is the last alphabetical. If I'm predicting something to be a weekday or a weekend, what would I be predicting? What would be the probability? The probability would be associated with the probability it is a weekday or a weekend. Very, very small, tricky thing right there. If I'm predict weekend, last alphabetical. Yep, and that's a 2-level prediction. So the probability would be associated with the probability it's a weekend because of the week D, week versus week E. And so very small, decent test question. The level of interest is the one that's last alphabetical. So we're predicting yes because yes is last alphabetical. It's completely arbitrary. It's just the way the algorithm works. You could reassign names of levels so that way you could put no as Zeno or Zo, and you could do that. Now let's look at the truth right here. And when we look at the truth, something interesting is going to happen. So we're going to go right here and say yes, yes, no, 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 no. With this right here, what is the accuracy of this model? What is the accuracy of this model? Who knows the accuracy of this model? First person, 1,000 points. What's the accuracy of this model? What is the accuracy of this model? Close. There you go, Jinning. You got it, Jinning. Jinning's right. It's 5-6. And notice the only misclassification in this model is the following. The only misclassification. Does that make sense? And so, and don't worry about that's just coincidental that the yeses are there. This is just the truth. Like when if we find out if that person would have bought or not. So we could have a model that has 100% accuracy, or this model right here would have the same 5/6 accuracy. Oh my gosh, I hate it. If you move it too slightly, it doesn't do it. If you move it too much, it'll delete everything. This model also has a this model right here has a my gosh, I can't think, has an accuracy also of 5/6. This model now also has an accuracy of 5/6 because it's right 5/6 of the time. Does that make sense what accuracy is? This model here also has an accuracy of 5/6 because it's right 5 out of 6 times. Does that make sense? And so this would be that. The thing I have circled right now is a false negative. Great, Toss, 1,000 points right there. Toss, you are totally right. That's a false negative because she predicted no and it was actually yes. So that's a false negative. So that I have now circled a false negative, and previously was a false positive. I think I had a false positive before. So that right there, is that the one we did previously? That is a false positive right here. That is now a false positive because she predicts yes and it's actually no. This right here is a true negative. This right here is a true positive. And here we'll put in another, we'll do the other combo, and we'll write it all in right here. So you can see, I hate it when it does that. This is really good review right here to know each of these and what they mean just in the visualization of the data. This right here is a false positive, and this here is a false negative. Because she predicted, the false negative goes, and it's pretty much precision and sensitivity, precision, and all that stuff right there. And you can see that in some of the graphics. They write that out. Here, I'll show you, Anisha, that might help you out. We don't use those terms. We're looking at that. Where is, I just saw precision on here on one of these. They talk about sensitivity and specificity. So if you, which is your false, there you go. And so this curve right here is showing sensitivity and specificity. So 1 minus specificity right here, and they're showing the false positive. There's the random chance model, the true positive rate, the false positive rate. So how often we have false positives, and we really want a good ROC curve like this right here. Like the better ROC curves are going to go whoop up like that. That's what we really, 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 really want. And we're going to see right here how to calculate. Does that make sense, Anisha, what's going on here? Because it looks like you've seen this in other disciplines, and hopefully it's kind of making sense. You got it? Yep. Like it's maybe connecting the dots for you. You're like, okay, I totally see what's going on right here. I try to use as many, because there's so many terms in so many disciplines. Every discipline's like, we call it this, we call it this. So what we have right here is a harder problem. Now, what we're going to talk about now is the, this is used a lot, like sensitivity, specificity, and precision, all that stuff. Yeah. And so what does AUC actually mean in context? So here's where we get into, okay, it's cool to have all these terms, but what does it mean? And that's what business analytics really focuses on. Like, what does AUC actually mean? AUC, take down this definition, is the percent of time the yes class gets a higher probability than the no class. AUC is the percent of time the yes class gets a higher probability than the no class. AUC is the percent of time that the yes class gets a higher probability than the no class. So AUC is the percent of time that the yes class gets a higher probability than the no class. And so we can figure it out first here mathematically. 1,000 points first person puts that in the chat. AUC is the percent of time the yes class gets a higher probability than the no class. And we can look at this. Let's look at this one first right here. This yes class right here receives a higher probability than the no class what percent of the time? This yes class right here receives a higher probability than the no class what percent of the time? AUC is the percent, oh, careful, Toss. AUC is the percent of time that the yes class gets a higher probability than the no class. Yes, exactly. So make sure to have that bit right there. AUC is the percent of time that the yes class receives a higher probability than the no class. This one specific instance, how often is this yes class getting a higher probability than the no class? Well, did it get a higher probability than this one? Did it get a higher probability than this one? And look at its probability. That's why I ordered the probabilities. Did this yes get a higher probability than this one? Did it get a higher probability than this one? Did it get a higher probability than this one? What percent of the time does that yes class right there get a higher probability than those no classes? 100%, you're right. And that's just for that one specific one, just that one. How about this one right here? This yes gets a higher probability than these no classes, what percent of the time? And that's why I ordered these. So this yes right here gets a higher probability than these no classes, what percent of the time? What percent of the time does that yes get a higher probability than those no classes? Look at the yeses probability and look at any of the associated no probabilities to see what percent of the time that yes has a higher probability than those no's. 100% again. Now we see where we have an error. Now we go here in this yes class, where this yes class got a higher probability. It did, or excuse me, the no's actually have higher probabilities. So, let's draw this with a different color here. All of a sudden right here, we see those where this yes only had 33%. Ishan, great job, 100 points right there. Yes, this one only has a 33% of the time that this yes gets a higher probability than these no classes. So when you think about this, we had 12 cases and, 9 cases. We had 9 cases and 7 out of 9. So 7 out of the 9 checks we did. So the AUC for this should be this. It should be that right there. So that's the AUC. That should be the AUC mathematically calculated. Now we're going to try to show this right here. I'm just thinking through in my head. I'm like, okay, got to draw out the graphic. We can do this. And let's see it right here. So let's see this right here. What we have right here is we have the graphic. We're going to take a peek at the graphic again because I've drawn this manually by hand a bunch of times. And we have right here the false positive rate. And there we go. So let's continue on right here. And what we're going to do right here is we're going to move down to the bottom graphic. And we should get 7/9. Because what we have right here, is when we go through the AUC graphic, it looks like follows. We're going to go right here, and we're going to go up 1, 2, 3, and these are our true positives. And down here at the bottom, so I'm going to take a quick peek again, because the bottom one is always the one that false positive rate. Yeah, because we have to move through those points to get to that. Okay, that makes perfect sense, theoretically. Okay, cool. And you'll see it, we'll get 7/9 when we draw this out. Because think if I draw a grid on this, how many boxes, and they should be equal space, how many boxes are in my grid now? Does everyone see my grid and how many boxes are there? Pretty easy to count the boxes. And you'll see we'll get 7/9 when we draw this out. 9 boxes. So let's start out. Going through my data right now, what do I immediately hit at the start of here? Someone classify this as a what? Someone classify this as a what? I immediately hit a what? What is that called right there? True positive. So we immediately hit a true positive, so we're going to go right like this. We're going to go up the scale. Then what do I hit immediately next? I immediately hit a what next? I immediately hit another true positive. But now, what do we have to start to go through here on this data right here? We have to start going through the no's. And so with this, we're actually going to start going over now. So we go over, and then we go over again right here. And now we would go up, and I'm just making sure if everything's accurate, everything should be accurate. And we go up and over, and this is where we hit, and that's where our false positive hits right here. And this is where we have 7/9 should be the area under this curve right here. We achieve 7/9. And this is the percent of time that the yes class gets a higher probability than the no class. So if you can see right here, we have that. False positive, true negative, false negative, true negative, all that good stuff right here. And we're going to see right here where we go through the data and we achieve this right here. And it's the percent of time that the yes class gets a higher probability than the no class. The yes class receives a higher probability than the no class 77% of the time. Now, what's really confusing about this, what's really like, well, why would we use this? So the big question here is like, why would we use this? The big reason on why we would use this is the following. The fourth row, yeah, it's a good question right there. So the fourth row right here, and that's, I'm just making sure, 1, 2, 3, 4. So we go 1, 2, 3, and this is where we hit, let me make sure, we're going through the false positive. Let me make sure everything's accurate right here. I should be able to, I might draw one out in R just to make sure, because my brain, wait, true positive, false positive, and then we're going through, because did I calculate AUC correctly? Let's pause here for a second. Did Brian make an error? I went all semester with no errors. Is today they may, probably made an error somewhere. Let me double check, make sure this AUC is calculated correctly. Let me think for a moment. So right here we see that if we have the AUC, it's the percent of time the yes class receives a higher probability than the no class. So we have here the yes classes, and if we have here, we only have one false positive. And the way it's plotted, because if you have no false positives, let me look at the graphic again. So my brain is like, false positive rate. This is the false positive rate we would expect by random chance. So that's the false positive rate we would expect by random chance right there. And the graphic, yeah, okay. So as you move through your data right here, this is where you hit your first true positive. This is where you hit your first true positive. And then nothing happens right here. And then nothing happens here. And when we get our first, we get our final false positive right here. Is that making sense? Because this is going from 0.4 to 0.5. This is a true positive. If we had accepted this, this would be a false positive. So you see when we have the nose right here, this is accurate. This would, to choose this, this would be a false positive. So we're moving right when we have the nose right here. We're moving, do you see how we go yes, yes, no, no, yes? And so this is where we see we would have had it right here if we had said that this was. So the way in which it's ordered right here is you go through yes, yes, no, no, yes, no. Does that make sense, Nitin? Does that make sense right there, what's going on? And we're looking at kind of how we would expect it to go. Fourth column, no is a true negative. And so right here, it is a true negative, and then this does not take into account true negative right here. So the true negative, the fourth column is a true negative, but this right here is kind of what we would expect by random chance. And then is this a true positive? Would this have been a false positive to plot it right here? So if we go right, shouldn't the graph go straight up? The graph right here on the fourth, so the main thing you focus on, what's interesting, so remember, here's where I think, and this is great, and thank you so much, because I'm 99% sure we're accurate. Please don't correct me if we're not. Since we're only looking at this right here, take a look at what we're looking at. We're only looking at true positive and false positive, which let me think right here. Now my brain's slowing down. True positive, false positive. So since this is the false positive, did I make an error? And I think I might have made an error. You're making me rethink this. Shouldn't the graph go straight up? Then, Brian might have an error. So let me think. The percent of time the yes class receives a higher probability than the no class is what it is. So when we look right here, we have that the yes class receives a higher probability than the no class. And we can do an easier version. I feel like I have made an error. Dun, dun, dun. For no, the fourth row, shouldn't it go up? Because I thought yeses were up and nos were horizontal. This makes sense with what I've drawn, but something is just like not clicking in my brain. Let me look at the notes. Sorry, everyone, for the Brian's brain jumped a moment. AUC. True positive, false positives. So we go right here. And you know what? We should be able to make, we could probably make a model and actually just take a look at it. There's a really good AUC, the AUC there. And when compared to a randomly picked, we would give the yes class model has 97% chance of giving the junk mail a higher probability than the safe. There we go. You're thinking wrong now. I know, my brain's just, it's one of those days where like brain's not firing on all cylinders. It's not like junk mail filter deletes 10%. And there's the ROC curve right there. I'm like about to cheat and go look at the video I did last semester because I know I got it right. And then I'm just like, what did I make an error on today? So let me just rethink something for a moment. Good, we're fine on time. Let me rethink something real quick. let me rethink. Okay. So it is literally defined as the percent of time the yes class receives a higher probability than the no class. So the yes class right here, receiving a higher probability than the no class, happens, am I incorrect that happens 77% of the time right here? And as we move through our data, we should get that these are false positives right here. So let me see, let me try this. Because I think I've got it drawn correctly here, but what we should look at is, let me put the way this is drawn. So these are the true positives, and these are the false positives. So the true positives right here, there's that many true positives. So there's only 2 true positives. And there's only one, is this a false positive? We predicted yes. Oh, and it's actually no. So that's a false positive right here. So there we go right there. And so that's, sorry, I think I made some grave errors today. No, I think the percent of the time the yes class receives a higher probability than the no class. So we gave those right there. And okay, let me think. Let me bring up the thing. Another question: how did you deduce the number 7/9 by looking at the table? Would your true negatives go up the graph vertically? The true positives is what is on this axis right here. The true positives, the false positives are down here on the bottom. So let's double check, because we only have one false positive right here. And then we have the true positives. So let's see. I think this is where, let me just think right here real quick. And so we only have, we need a bigger data set. Let me try one last thing right here. We're going to try another attempt at this. Brian's brain's going to go 100% right here. So 2 seconds, and then we'll go back to that problem. Let's try a data set right here with the following. Let's go here to prob, and let's go to truth. I can usually put truth there, and let's go to predicted. So let's go 1, 2, 3, 4, 5, 6, 7. And when we do this right here, we'll go to 90%, we'll go to 80%, we'll go to 70%, we'll go to 62%, we'll go to 40%, we'll go to 33%, go to 20%, we'll go to 10%. So predicted is going to be yes, 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 no, 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 no. And then the truth is going to be yes. For the first one right here, we can just do 100% AUC. If I were to do yes, 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 and the yes class, this should still be 100% AUC right here, because the yes class gets a higher probability than the no class 100% of the time. I think we'll double check all the theory here in just a second, but this should still be 100% AUC, because the yes class gets a higher probability than the no class 100% of the time. So the truth is that those are yes, and all the yes classes, it might be because I flipped my columns, and so the yes class right here receives a higher probability than the no class 100% of the time. But let's make an error in the AUC now. Now we're going to make an error in the AUC, and we're going to compute it again and make sure we get it correct. Now let's go here and put no, no, yes, yes, yeah, or my gosh. Yeah, we'll do no's from the bottom down. It'd be a really bad model if I did that. Okay. So now, and we'll put a yes all the way down here at the bottom. Okay. So now the yes class does not always receive a higher probability than the no class. Does that make sense? The yes class is not always receiving a higher probability than the no class. So when you look at it, does the yes class receive a higher probability than the no class? We want to figure out what percent of the time when this model makes predictions that the yes class receives a higher probability than the no class. Who's with me on that? This one should work. We got this example. We're going to do it. So we have here, what percent of the time does the yes class receive a higher probability than the no class? So when you look at this right here, I think I know why I made my error. So when we look at this right here, we have right here that there are 3 yes classes and 2 no classes. I think it's going to be 66%. I think that's going to be right there, Jordan. Jordan, that is what I'm thinking also. And I kind of wrote it this way, so it should work this way right here. So let's take a look at this. And this should work now. Yeah, okay, I think we finally got it. Then we'll go back to the other example and we'll fix the other example. So what we have on the bottom is our true positive versus our false positive. So the graph should have on it true positive versus false positive. So let's go right here and let's go true positive right here. True positive, false positive. So how many false positives do we have? We have here, when it comes to false positives, I believe we have 2 false positives. So the false positives are going to be errors made right here, where we predicted yes and it was actually no. Boom, false positives are right here. So there's our false positives right there. And when you look at this graphic, let's start going through our true positives. How many true positives do we have? We have here 2 true positives. So we have here a true positive here, a true positive here, and there we go right there. And we should have that last little bit. The false positives are right there. And then we have here a true positive at the bottom that it's actually the yes class. And let's see, there are true positives. So when we go through the true positives, the false positives, and I feel like one thing is off because as we go through here, why is my brain breaking today? I literally did this like 10 times last semester. And then, so when we go through the false positives here, because that is where the error is happening. AUC, Connor, you saw me do this 10 times last semester. Connor, what error am I making? Why is my brain not working 100% this morning? What am I doing wrong on this graphic? The numbers down here are off. We need the true positives and the false positives. And should we be plotting 1, 2, 3, and then this one right here? Because we should get an AUC of 66%, which I feel like there should be one more true positive right here, which is where I feel like if this had this last thing right here, and so my brain is just not, sorry everybody. You ever have one of those, it's just one of those off days. So the third point is incorrect, I believe. So, okay, Connor, you're TAing me right now. How many do I need? It would make sense that this needs to be a 2x3 grid because the AUC here is 66%. Like, so the AUC here is 66%. And how many false positives do we have? So how many true positives do we have? So if the AUC is 66%, it only works out mathematically a few ways. So might have to like review and just like my brain's just like, but I can tell you for certain the AUC is 66%. So the true positives are the ones we predicted where they're actually the ones we want them to be. I'm just taking a look. And the false positives, let's just do this. So if we have true positive right here, and so we should have 1, 2, and then the false positives right here. So what does the true negatives and false negatives count on the graph? Are they considered? That's where, sorry, my brain's just like, let me see here. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And then 1, 2, 3. So let me see something right here. Good news is we don't have to draw it by hand. 1, 2, and then 3, 4, 5, 6. And then we would go over here. But then we have to get through all of our true positives. So it has to go up. And then this right here would have to go up because it does reach 100%. So it's when you go through the data, it has to reach 100% right there. Okay, wait. That's it. Okay, I think I just figured out in my brain. Okay. So when you go through your data right here, you would achieve the final true positive right here at the final point at the bottom. So you would achieve this right here, and you would go right here. And so this should look like the following. It should go up, 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 and then over, and then up, and then it finally reaches there. And so that's the way it should look, but that's not accurate to what it should be. Or is it? I am sorry, everybody. I am sorry. My brain's just not 100% today on it. And so I should be able to draw this out, and we should be getting 2/3. And if it were to go over right there, it'd be 2/3. But you always achieve at the AUC, just graphically, you always achieve where it's gone to 100% because it's gone through 100% of the data. It's achieved all the true positives. So at the point, let me just think for a half second here. When it's achieved all the true positives, it's achieved all the data right here. And so it should just be going, because there's the false positive rate. It's just the way I have it drawn out with it being weird. Because when you've gone through, here's just one of those weird things, because maybe the curve can do this. You just wouldn't see this. You wouldn't see one rated this low. And then this curve should look like, you know what I think? I think I just figured it out. My gosh. You ever have one of those things where you just get like your brain, you just get like anxiety and then your brain just turns off? That is literally what has happened to me today, is like my brain just like turned off and it just like, yeah. So what we should have right here, if this is 2/3, we should have the following. And we should have a graphic that we go right here, and there's only one false positive on the graphic, the false positive being right here. And when we go through it, we would go through our data and we'd hit the false positive there, which means we would go up, and up to here and go over. And this would be the AUC curve. It would go like this, but the area underneath it would be 2/3. So that's what it should be here. Now let's change the thing just slightly. Let me see if I can change it and make sure it works. I did this like 10 times for everybody last semester, and now brain. So now let's go here and let's change this to, this is a true positive, and this right here is going to be a, whoops. So that's a true positive, and that's a false negative. Oh, my brain is just not. And right here, we'll put a, well, the true positive, because if the truth is there, wait a minute. Okay, good. Then these have to be, oh my gosh, these have to be predicted no, and let's predict this yes, predict this no. So all of a sudden, Brian's brain broke on AUC. Yeah, so Wacky Wednesdays is full. Oh my gosh, sorry I've completely lost everybody. I'm sorry. So yeah, Wacky Wednesday is in full effect as Brian's brain just melts through his ears right now. So 2 seconds, Sarah. The graph right here is the ratio of your true positives to your false positives. And what do we want? Like, my brain's just telling me what we want. Let me show the graph and let me explain what we want on this graph. You want in this graph to go through all your true positives to start. You want your true positives at the start. Does that at least make sense theoretically to everybody, that you want your true positives to be what you go through at the start? Like, who's with me on that? Because we should get this mathematically calculated. I might have to put it down for a second and just review what I'm doing right here. But when we look at here, this is the no skill, just random chance model. Here's our logistic model we're building. Does that make sense? We want our model to go through the true positives. And if you look at the way it kind of goes over and stuff like this, there can be different amounts. And look at this. This is confirming that you have to go through more of the data right here to finally receive a false positive. So you don't count everything as you go through the data. I think it's the smaller data set that's getting to me, because this went through a whole bunch of data that was probably just true negatives. So right here, these were either true negatives or they were false negatives. These were either true negatives or false negatives. So this is where it goes through a bunch of data. This is going through a bunch of data here, where it's going through two true negatives or false negatives. It's literally your true positive to your false positive rate right here. Does that make perfect sense? Like my brain's just telling me the theory every moment on this. It's like, here's how it works. Here's what's going on. And if you look, we're going through more data right here where we don't see. So trues go up and falses go to the side. Bingo, Adam. Yeah, our brains are working. We're getting our brains turned on. I was just seeing if you guys could figure it out this whole time. I was just trying to trick you. No, my brain was broken. It happens every once in a while to all of us. So thank you for bearing with me. I know we ran out of Red Bull. So does the straight line always have a slope of 1? Yes. Ishan, this always goes up like this. Whenever you hit a true positive, it goes up. And it looks like they hit a bunch of true positives here because they're going up. And then they have to go through data to get to the false negatives, or they're going through data right here to get to the true positives. So when the line goes up, you're going through true positives. And then when the line goes over, you're going through false positives. So what you want is you want to go through all of your true positives immediately. You want to go through all of your true positives as quickly as possible. And I'll draw one out tomorrow. I'll draw one out after class. Does the x-axis include false positive rates, false negative rate, and true negatives? The x-axis is just the false positive rate. And I think so the line represents the true positives and the area under the curve is false positives. It's the percent of time. So Anisha, really good thing right here. This is the percent of time that the yes class receives a higher probability than the no class, key definition right here. And if this goes straight up, then what would that mean? Start drawing from the top down. Yeah, Amid right there. What's my mistake? Here, we'll go back to that in a second. If you go straight up, if you were to go straight up, you would have immediately gone through all your whats. If you go straight up, you'd have immediately gone through all your whats. So that should make sense right there, your true positives. And that's what you want. If you go straight up, you'd have gone through all your true positives. And then we could go through our false positives. So what we'd see right here, if we go straight up, let's do this theoretically. We're going to draw out a new graphic where we're going to go straight up, and then we'll have our false positives. So let's do this theoretically right here. Let's make a really nice drawing. Do a really nice thing right here where we can easily read what's going on. Here we'll go to insert again, insert table, and we're going to do this really nice and really neat, and we're going to conquer AUC today. We got this. So we'll zoom in so people can see it, and then we'll center it, and let's see this. Okay. So what we have right here is we have the probability, and we're going to put the probabilities nice and neat so everyone can see what's going on. Could you explain what does it mean by yes class? That just means we're predicting something is yes. Like, is it junk mail? We'll predict yes or no. So we're trying to predict if something is junk. So the yes class means we're predicting yes, it's junk. Like we can say, let's predict junk mail, yes or no. And the yes class would be things that are actually predicted to be junk. Does that make sense right there? So the yes class, everything is classified as true positive. What do you mean by that, Connor, again? Explain, sorry. Everything is classified as true positive? Yeah, oh, you're saying for the 100%. Everything we got accurately, and we got through all our true positives. So here's where the switch is going to happen right here. And we want that the yes class receives a higher probability than the no class 100% of the time. So we have here true positives, and we have here false positives. So we have here actual. We'll put that actual. So this is actually yes. And this is actually yes. This is actually no. And this is actually yes. And we'll do it where it gets a higher probability. The yes class gets a higher probability than no class 100% of the time. So this right here has the yes class getting a higher probability than the no class 100% of the time. So this is the predicted, but this has an AUC of 1 because the yes class always has a higher probability than the no class. So this would be no right here, and this would be no, and this would be no, and this would be no. But the yes class receives a higher probability than the no class here 100% of the time. And when we move through, we have no, let's see here, false positives. So the false positives would be things where we have things, well, we do have one, wait, false positive right here is right here. And so we have true positives, true positive, true positive, false positive right here. And so there we go. When you refer to the yes class, are you looking at the actual? Yes. Oh, this is what something actually is, and I think we just made sense of it. I think we're good. Let's draw this out, because I don't know why my brain was just breaking today. And why don't I have my pens now? Really? Don't steal my pens. Can I now draw inside of a table? There we go. Okay. So now right here, the way this works is we have 3 true positives and 1 false positive. So now, with these true positives right here, we go 1, 2, 3. And this graphic goes the following. 1, 2, oh my gosh, not the first one. 1, 2, 3, and then goes over to this false positive right here as you go through the data. Does that make sense right here? And this confirms that this has an AUC of 1. But then let's go down here and let's put an actual down here at the bottom that it was actually yes. So now we have a true positive all the way down here at the bottom. So this is a true positive down here. So it's a actual something that was a true positive. So this is actually a true positive right here. So we don't plot true negatives and false negatives. Correct. This is an actual something that is, and let me just think right here. The yes class right here, let's just show it mathematically. And so if we were to go through and the true positives, because the yes class is not receiving, so my brain is just not working. And then we would have to go through the rest of the data to get to that right there. I just wanted to draw it out for me. Can I do the AUC? You know what? We're going to put it into R. We're going to do it right here. Let's go into R. Let's get R to solve it because, sorry, my brain is just not firing on all cylinders today. Very sorry. This is my quick apology. Just brain. We got Connor here to help out. Connor, how are you doing today? So let's see. Let's make some predictions right here. And let's get the ROC curve on the screen. So ROC curve. So here's our ROC, and we should see ROC holdout. So this will plot the ROC for us. And we can go right here and let's see. So we have the ROC is going to take the actual Y values and the predicted values of the model and all of this. Okay, good. We're going to take this code and we're going to have fun with it. And ROC is in the PROC package, I believe. So we need to load PROC. And there it is right here. And now we should have the ROC code. We do have the ROC code. And then when you analyze how the ROC code works, let's hop in here and take a look. What does the ROC code take? It takes the actual values of Y. So we need the actual values of Y right here. And then what do we have? We have the predicted, and we're getting a probability out of it. So all the ROC code is taking, when you look at this ROC code right here, is just taking the actual and the predicted right here. And this right here is going to take from it just the second column of it. AUC was super interesting, but yeah, I know. And this is just, and we went through it so many times. If you just review the lectures from last semester, you'll see me just like, and all of a sudden today, my brain just overheated. And then it hasn't happened to me in a long time, but if anyone ever have that, if you make a mistake and your brain you just get anxiety. So very sorry. This is the first time you're seeing Brian like being like, and your brain just is not working. So we should be able to, here's where we're gonna get everything working again. So we go here with the actual, and the actual needs to be, we should be able to do like yes classes, and oh yeah, happens to you all the time. You know what I'm talking about, exactly. And here we'll do this, we'll make the model, we'll show what it's making right here. So let's show what this model is making. We're predicting the Y variable. So let's show a logistic regression right here. Let's hop into a logistic. And we're going to do a model today. That's what we're going to do. So where is our logistic? Where is logistic? Regularized logistic. Sure, we can do a regularized logistic. And oh, we're already there? Sure. Yeah, there we go. Vanilla logistic. Cool. So we have here a model. And let's predict something in this model. So in this model right here, we need to make predictions. And the predictions we're going to make are going to be on a data set. So let's go here to data. And we're going to do something right here. We're going to take survey 10, And we should be able to do regularized logistic regression by doing the following. Let's go in here. We need to make first of all, we would clean the data, but we did that yesterday. Second of all, we're going to make a train rows. So train rows are going to be, so make sure you know these types of things, is going to be a sample of 1 through the number of rows of survey 10, and we're going to take, let's say, 80% of them. So we're taking 80% as our training data. So this is key stuff right here. We are going to take these, store these into train rows, and then we're going to take our train data, and we're going to go here to survey 10, and we're going to drop this in, and then we're going to go here, and we're going to copy twice, and we're going to go here to holdout, and the holdout right here is going to be not the train rows. Does everyone understand? I've just made training data, and I've made holdout data. Does that make perfect sense? Everyone follow me on that? I've made my training data, I've made my holdout data, and now I'm going to predict gender right here in the model, which we should get, that this should run, everything should be good. We have the fit control is not set up, so we need the fit control. So the fit control right here is going to be, because TR control goes fit control, we need to go and we need to do the AUC fit control. So let's go back up to the very top where we have the fit controls, and that's all those examples. And let's go to where we can set the fit control. So train control for classification. So here's where we set, this is so key. If I want to fit on AUC, I have to use the following fit control. So I have to do this right here. Did not find that. That's because library caret's not loaded. And there we go right there. And so train control is inside of there, and now it runs. You have to choose the fit control you want based on what you're fitting your model on. So please make sure you choose the proper one based on it. We talked about that a lot yesterday. So make sure to choose your proper one right there. Gender, let's go back to here. And now that we have our fit control selected, we are good. Preproc is going to turn everything into what? Show you're following along, 1,000 points first person. Who's got it right here? Who's got what the preproc is going to do? The preproc is going to do what? The preproc is going to do what? The preproc, Z scores, 1,000 points right there. Jordan, Connor, Yazi, and Anisha, and Madeline, you guys got it. Thanks. You give me back that energy. We know what's going on. Fitted probabilities numerically 0 and 1s. That's just warning methods. Cool. That's fine. We should be all right. Summary of the model. We get a summary of the model right here. We've got all the coefficients. Lots of fun coefficients. Model results. ROC is 99.47. So the key thing is that we should know that this model correctly predicts the probability, or correctly, the yes class is giving a probability 99.47% of the time more than the no class. The yes class is properly ranked. We properly rank the yes class 99.47. It properly receives, it gets a higher probability than the no class 99.47% of the time. This is just going to give us on the holdout. Did we not get it? Oh, because we don't have the variable name. So we didn't put in the Y variable name right here. So it should work now. There we go. That's on the holdout. Accuracy on the holdout. But now we have to get the ROC on the holdout right here. And so now we can get the ROC on the holdout, but we need the Y variable. We don't need the Y variable, do we? We should be good. And AUC, no valid provided, arrow in ROC, predict model, new holdout, type prob, no valid data provided. New data equals holdout, type, what did, oh, Same thing I didn't do before. There we go. And on the holdout, it works really well. If you notice on the holdout, we get an ROC of 98%. Now, when we take a look at this right here, we have right here an ROC. And let's take a look at this. We're predicting gender. And so we've got male and female right there. And then we've got here the predictions that it makes, but we're taking just the probabilities. So this is how it figures it out right here. It gets all the probabilities associated with that. So what we can do now is we can play with this code and see what's going on. So in our code, this is where we're getting serious. Brian, true class is true probability, and oh, it is that right there? And false negative. So that's what it is. Ahmed, 2,000 points. So that's the error we're making right there. True class is, so when we should be moving up and over, right? So I'm not putting enough lines on the graph, am I? So Ahmed, you're going to be our helper, because here we're going to put this in. Does everyone see here we have right here, this right here, And what percent of the time does the yes class receive a higher probability than the no class? And the yes class, this is 100%. This is, it receives it 3 out of 4 times. And this receives it 1 out of 4 times. So it should be an ROC, if I'm calculating this correctly, of 75%. That should be 75% of the time the yes class receives a higher probability than the no class. This should be the ROC of this curve. And when I draft it out, it should get 75%. So figuring it out mathematically in my head, and if you did it as quickly as I did, we should get an ROC of 75% right here. And so if there is 8 total lines on the graphic, which I'm thinking there might be now, and let me just try one thing real quick, because we just figured it out, and then I'm going to put it into R and let R solve it. 1, 2, 3, 4, 1, 2, 3, 4, and then so up, and then over, and then up, and then the only way I'm just trying to, it's like a puzzle, and then over. You see, that's going to do it. That's 75%. Ahmed, is this correct? That's 75% right there, because if you take this block and place it over here, that's 75%. I don't get this 75%. Can you explain how we're getting it? So the way in which, and this is the way I always calculate in my head, and this is where should be, I agree with Ahmed, true class should be all the predicted correctly, both sensitivity and specificity. So there we go. And so Anisha, is this looking correct to you right here? And we'll review this again tomorrow. Sorry that today's class was Brian's brain overheating. We're going to call this today's class Brian's brain overheated. But this right here calculates to 75%, which is what I would expect it to calculate when I know how to talk about it. And so Nitin, the way it is when you look at what percent of the time the yes class receives a higher probability than the no class. Let's look at this one right here. This yes class right here gets a percent higher than the no class, what percent of the time? So that yes class right there, what percent of the time is it ranked higher than these no classes? Yep, and Connor's showing it too. That yes class gets a higher probability 4 out of 4 times. Does that make sense? And so then this yes class right here gets a higher probability what percent of the time? This yes class gets a higher probability what percent of the time? That yes class gets a higher probability 100% also. This yes class right here gets a higher probability than the no class what percent of the time? This yes class gets a higher probability than the no class what percent of the time? And look at like how often does that yes class get a higher probability than the no classes? What percent of the time does that yes class, the one I've circled right now, than the no classes? This will show it right here, Vedrina. What percent of times does that yes class right there get a high probability than those no classes? And I think that's the graphic. I just want to see my ROC curve graphic. 3/4. Yep. That's 3/4. 3/4 of the time, because it does not get a higher one than that one, and then there's 3. So 3/4 of the time that yes class. So that would be 75% right here. And then this yes class right here gets a higher probability than these no classes. What percent of the time? What percent of the time does this yes class get a higher probability than these no classes? What percent of the time does this yes class get a higher probability than these no classes? 1/4. And so if you look at the math right here, the top part of this equation is everything there, and then we have 4 total times that we did this. So when you do this, you'd get 300 divided by 4, which is 75%. And then we should have the correct drawing right here on this. I believe that's the ROC curve. My brain just broke on how to draw it today. And what we can do right now is, for the last little bit of class right here, we're literally going to enter in this data. We're going to take this data right here, and we're entering 90, 80, 70. So we can just go 90, 80, 70, 60, 40, 30, 20. So we skip 50. Okay, cool. And so we're going to go here to the predict. We can just call this prob. And we're going to go and make a vector of 90, 80, and then I'm going to try to draw, I'm going to have it plot the ROC curve, which we should have the graph for that too. 60, and then 40, 30, 20, and 10. Because when you look at this right here, the predictions right here are just probabilities. So we're going to put that in the second part. That'll become the prob. And then the gender, when we look at gender right here, we're going to just put in, because ROC is going to work either way, we're going to put in the yes versus the no class right here. So we have here that ours were yes, yes, no, yes, no, no, yes, no. So it's kind of, okay, I see the pattern. So I think I see the pattern. Let's hope we get it correct. And we have here actual. So this first part is the actual, and I think we can just abbreviate with like yes, and then it's yes again, and it's no, and then it's yes again, and then it's no, and then it's no, and then it's yes, and then it's no. The pattern was like, it kind of flip-flops. It's empty today. It's yes, yes, no, yes, no, no, yes, no. And we can double check this. We go back to where it's at, and we double check that we have the yes, yes, no, yes, no, no, yes, no. And we have this right here. So we go to the probs, we go to the actuals, and then we go to the ROC curve, or we go to the ROC, we go to prob, and we go to actual, and we get error. So we get, oh, we need to go to actual. Actual, go to prob, and we get right there. There it is. We have confirmed it is 75%. The only issue was on the drawing. We figured it out mathematically. We've been correct all today, I believe, with everything we've been doing. We'll look here at the other examples, and we'll get the ROC curve to draw. So keep staying if you want. We'll just go a little bit over. We calculated this one right here. We'll get all of these ROC curves to draw. We're going to draw out all these ROC curves. We're going to see them all visually here. We calculated this one to have a what? This one right here was calculated to have a what? What was the ROC of this one calculated to be? So we have here, yes, 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 no, no, no. What is this one calculated to be? This one has an ROC calculated to be what? 1. Yep, because this one, the yes class always receives a higher probability than the no class. So this had an ROC of 1 right here, and it should be pretty obvious. We could take and do the same thing right here. And so we go right here, and we can just delete off some of these, because I think we only had... And so now we see that we have yes, yes, and we have 3 no's after that. So the yes class always receives a higher probability than the no class. Yes, 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 no, no, no. And even though the no is improper, if you notice the no right here has a 60% probability. So now are you looking at the predicted column? It's basically, because this should still have an ROC of 1. Boom. Right here, we're not looking at the predicted. It's just what it actually is. If you notice right here, so Nitin, that's so key to notice. When ROC does calculations, it looks at your probabilities, and then it looks at what it actually is. So it can figure out the predicted, but the truth column is on the right side. Yeah, that's when I plotted it that way, I made, oh, wait. Yeah, okay, this one does not have an ROC of 1. You guys caught it. So, yep, so this is yes, yes, no, no, yes. And then what was the ROC we calculated here? We calculated that this was an ROC of what? What should the ROC be for this? In this one, the yes class receives a higher probability than the no class, 7/9, right? Does everyone see 7/9? So we need to move this yes. Let's do it in the code. We're going to move this yes over to here. And now we should get an ROC of 0.77. And there it is right there. We are doing it correctly. I just can't draw the graphic today. Brian can't draw the graphic. He can't do the graphic by hand. But we are getting the right answers. Does this make sense? So as much as like my brain was overheating, everything I was saying was accurate on what it means. And so when you think about like what does it mean, it literally means the yes class receives a higher probability than the no class 77% of the time. Does that make sense when you look at this right here, that the yes class received a higher probability than the no class? Let's do it. And we're going to get the graphic to draw. Ahmed, we're not giving up on this. Like, we are not giving up. We have confirmed that Brian really hasn't said anything incorrect today, except Brian can't draw the graphic. Let's see. We should be able to plot ROC and R. Like, why does it not? We do have a code in here, I think, to plot the ROC. So plot ROC curve in R. My brain... It's in PROC. So some ROC package, CRAN has a package for it. Here it is, right? That's not ROC curves. Here's a, ooh, that's a pretty ROC curve. So there we go. Predicted and performance. Plot. Wait, that's not what we want. That's a ridiculous ROC curve. So ROC curve. Is it just ROC curve? Class scores. The argument's right there. Curve equals true. Plot ROC. Plot ROC. We're going to draw this out here in just a second, because it should just take the two objects. Class. Oh, there's the class labels. Score. Okay, wait. So what package is this? ROC it? ROC. Install package ROC it. We're going overtime. And so here we go. ROC int, score, and we're going to store this object. So we've got the score it got, and then we got the class label it actually is. Okay, cool. So we've turned on the package right here. We got the ROC it. We've got the score it actually has, which that's the first argument. So the score is going to be the probabilities, and then the class labels are the actuals. And it likes it, and it does it. There we go. Tell me I drew this perfectly. Tell me I drew this out exactly the way it should be. Here it is. Here's what it shows. Here's what I show. Look at that. And that is at the 2/3 point. We just drew it out. I was drawing it correctly. So this is the correct drawing right here. You can use the caret package to tune for false positives, correct? In that case, you would still want a higher ROC. Yep. You can tune different ways with the caret package. Yep. And you go right here. So if you look at the data we have, and it's how much data we're going through. Optimum index point right here. So as everyone see, the drawing I made right here is 100% accurate to it. You might say, well, it looks a little different. It's because this right here. So we have confirmed Brian is drawing these accurately today, because this right here for this, and it's saying, there we go, false positive rate, false negative. We're going to put this graphic right under here. This is Brian's prize for the day. Brian's brain overheated. So wrap text, behind text. And this is the actual drawing of it. So we were 100% right on our drawing on it. And so when you notice right here, so this is the data right here again. We don't have to worry about what it predicts. It is related to the probabilities right here. But if you notice when it's going over, there would be 3 spots. So you have to go over through the data. And you know what I think it does? Here's the thing, is when you go through the data, so it continues on. I think that's where my brain broke, is when you're going through the data right here, because that's just like the thing right there. Like this is 100% accurate, because we go yes, yes, no, no, and then you've got a true positive right there. That's where it goes up, and then you've got the no right here. Is this making sense, Phaedrina? So when it goes yes, yes, no, no, yes, no, and it's by ordering of the probabilities. So you actually hit a true positive right here, and this is how it's drawn right here. And so the true positive rate right here, it's like at this point. So what I want you to think about this, when this graph reaches 100% right here, what amount of your actual positives have you gone through? And don't worry about the percents. That it's not saying we classified it as something that is accurately classified. It's just saying it is actually a actual truth. It's not saying we properly ranked it. And I think that's where the confusion is, because it is hurting my mind a little bit too. It's not saying please show the table with the plot. Right. Okay. Yeah. So everything here is accurate. You can tell me to zoom in, but this data right here, I do have the numbers a tiny bit different, but they're still in the same order. It matters that this is above 50%, above 50%. Like watch this. If I change this to be a yes right here, this will drastically impact the ROC. Now the ROC should be the yes class receives a higher probability than the no class. I think 75% of the time. Yes, the yes class receives a higher probability than the no class 75% of the time. And so we should see, that should change it right here. And there we go. Okay, I was like, why isn't it showing up? So you see, this is 75%. This is 75% right here. You can tell because this is a quarter. This is a quarter. Do you see that right there, Nin? That this is, and we'll get 75%. So that's underneath the graphic right now is 75% of the area. So a Y goes up and the N stays flat. Yeah. As you go through the nose, it stays flat. So if you notice, it goes, we have the yeses going up. So up, up, and that's why it's at 50% right here. So it goes up, up, and then it goes over, and there's only 2 no's. So you only go over as many no's there are. So every time you see a no, you're going to go over to the right. And when you see the yes, you go up and up. So what's confusing here about this graphic is that there's not 2 spots. There's not 1 up, 1 over. There's actually up, up, over, up, up, over, up, up, over, up, up, over. Does that make more sense, Nit? And I think we finally got this down. Once again, I usually calculate in my head and understand the percent of time that the yes class receives a higher probability than the no class. And so, sorry, we will review this again tomorrow in a much quicker and more concise fashion. That's what we like to see. I went through, like, I just want you guys, hence we use the truth column to draw this. Yeah, exactly. We use the truth column because it's the percent of time the yes class receives a higher probability than the no class. So when we look at it, it's like, okay, what percent of the time was the yes actually getting a high probability? What will really mess it up is this, because what's going to happen immediately to the graphic now, because a no is there at the start. Since a no is there at the start, the graphic's going to immediately do what now? Since a no is there at the start, the graphic's going to immediately do what? And that's 0. Let me see. That one is 66, 1/3, 1/3. So that's 2/3. It's 4. That's 4/9. I think this ROC is 44%. I think it's 44%, or it's 50. I reversed it in my head. Let me think. Wait. Let me make sure. Is it calculating that correctly? Because it's saying the ROC is this. Ooh. Oh, I think it's, wait, you see it says actual no right there. And yeah, because it's flipping it, because it's, you know what's interesting? If you have a model that makes 100% wrong predictions, if you have a model that were to make 100% wrong predictions, is that a great model? This is a very confusing thing, which I think, if you had a model that made 100% wrong predictions, how good is that model? If your model was always wrong in predicting, how good is that model? Like, if you have a model that's always wrong, how good is that model? Like, if you predict if your team's going to win and your model's always wrong, how good is that model? This is a very confusing theoretical thing. And I understand why it did this now. If you have a model that's always wrong, how good is that model? That model's amazing. If your model's always wrong, it's amazing. You just have to know it's wrong. It's perfect. Exactly. So, yeah. And that's why, if you notice right here, the ROC curve is along the bottom, but we still get an ROC value of 1. It's just that R is being smart enough to say, well, wait a minute, you would just take this and flip this right here. We could do a more, here we'll do another, we'll extend this and we'll just talk through this and I'll tell people to, so that's an ROC of 1 also. Here we'll do, we're going to do 10 numbers. So let's do a sequence. We're going to do a sequence going, we don't need to concatenate now. We're going to go a sequence from this to this by this. And that sequence right here is, I think, more than 10 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that. Okay. So now we have, if you look at what this graphic's going to do now, when we draw this, we can think about what it's going to do. This is going to make it go up, up, over, over, up, up. Now let's just finish off with some overs. Okay. So we can draw this out ourselves. How many more do we need? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So the way this works is the places we will go up is we will have how many spots we can go up right now. We'll have how many spots we can go up. How many rails are there on this ladder going up right now? who knows for 1,000 points bonus off 0 points, who knows how many rails there are going up? There's 4 rails going up. There are 4 rails going up. And how many rails are there going over? How many rails are there going over right now? How many rails are there going over on this graphic? On this graphic, there would be how many rails going over? There's 6 rails going over. So when we go here, we're going to draw a graphic with 4 rails going up. Look at this. The Red Bull kicked in. We're going to go 1, 2, 3, 4, 1, 2, 3, 4, 5, and 6. And so let's take a look at this right here and see what happens. So we have here, yes, yes. So yes, yes. Yes, yes. And then we have here, no, no. Then yes, yes. No, 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 no. And then yes, yes. Oh, wait, and then did we do it? Was that it? And this all no's? Yeah, sure, that's it. Okay. Yes, yes. And then no, 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 no. Okay, so when we draw it, we should get this. But take a look. You can probably figure out the ROC pretty quickly from this by graphing it and doing this to it. And can anyone figure out the ROC pretty quickly from this? Can anyone figure out the ROC under this curve pretty quickly and accurately from this now? Can anyone figure out the ROC? Are the probabilities always going to be sort of from, yeah, we generally, if you're calculating it, if you're going to, they don't have to be, but, you know, just if you're going to, when we put it in, the y-axis is sensitivity. How do you define sensitivity? Oh, man, I don't, Anisha, definitely we'll look it up, and it should be 5, 6 right here. I don't use sensitivity as much as specificity. So sensitivity, I think it's just your true positive rate. I'm pretty sure sensitivity, here we'll Google it, like what is sensitivity? I think it's just your true positives. And then the bottom axis is 1 minus sensitivity, 1 minus specificity. So what is sensitivity? What is sensitivity and specificity? So when you look at, in medical diagnosis, test sensitivity is the ability of a test to correctly identify those with a disease. So this is when it gets it right. And the specificity, whereas the test is the ability to correctly identify those without the disease. So these are the yeses and these are the nos. And you want to go through your yeses immediately before going through your nos. So we want to go through our yeses immediately before going through our nos. And this is 1 minus specificity. I think I saw in some other graphics. Let me see. There was a graphic that showed that. It's like in medical research, they use sensitivity, 100% minus specificity. So this is the complement of specificity. So this is your sensitivity right here. Sensitivity, this is the actual yeses, the people who are actually have the disease. I know, like I want to make it everyone for it to make sense. And we'll show the graphic here. And then the bottom is 1 minus specificity. So specificity is finding the people who are nos. So it'd be everything but finding the nos. So when you think of 100% minus specificity, it's everything but finding the nos, which means we find things that are ranked incorrectly, but then also that would also mean we could find the yeses. That's where I think specificity is true nos. Yep. So this is not the true nos. So this is the true nos. This is the true yeses, i.e., and then it says here, so this is the false positives, because either something, so you either have the true yeses, or you have things that are classified here, and you see we're going through the nos right here. It says a bit about it on slide 86 in our notes too. Yeah, we should always look at the notes. Dr. Petrie made amazing notes. Let's go look at the slide 86 right here. So right here we have here the ROC curve, receiver operator curve, shows the performance of classifier predicting yes and no for the full range. And we have here, right, it plots the pairs of true positive rates, sensitivity, and the false positive rate, 1 minus specificity for various pairs and thresholds, and connects them with a curve. So once again, it's 1 minus right there. And when we draw this, we should be able to draw it, I mean, decently. It took me a while today. Sorry about that. And when we draw this right here, we get the exact drawing we have. Does everyone see my drawing is exactly, when you have a true negative, you go to the right. You focus in on, yep, so you focus in on if it's the no class or the yes class. Does that make sense that we went up, up, over, over, up, up, over, 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 over? Does everyone see the pattern right here? And the pattern is up, up. And I have them ranked by probabilities. If I change the probability rankings, it'll change the way it's done, but I have this ordered by highest probability to lowest probability, so it works this way. Is that making more sense, Ishan, that you go up, up, over, over, up, up, over, 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 over. And that's how we were able to draw this out right here. So we were able to draw this out right here before graphing it. And then we can also go right here and we can see it's 5, 6. So if you were wondering, that's how people were saying 5, 6. And that's how we get the ROC right there, which this is the percent of time the yes class gets a higher probability than the no class. Let's take a look. We have 4 yes classes. Does everyone see how there's 4 yes classes? What percent of the time does this yes class get a higher probability than these no classes? This yes class right here gets a higher probability than these no classes. What percent of the time? It gets a higher probability than these no classes. What percent of the time does this yes get a higher probability? I know, right? No, it's 100%. How about this yes class right here? What percent of the time does this yes class get a higher probability than this no, this no, this no, this no? This yes class has a higher probability than these no classes below it, 100% of the time. What percent of the time does this yes class get a higher probability than these no classes? Well, look, we got 2 here and 4 here. So what percent of the time does this yes class get a higher probability than these no classes? This yes class right here, it gets a higher probability than the no class. What percent of the time? 4, 6. How about this yes class right here? Also 66%. So guess what? We have 100 plus 100 plus 66 plus 66. And just due to decimal differences, we still get 83. But if you're like, well, wait a minute, why is it not exactly? You can just carry out more decimals and you will see it is now that. Does that make sense right here, how we're calculating that the yes class gets a higher probability than the no class 83.33% of the time? And that's one of the important things. That's why business analytics focuses a lot more on what does it actually mean. That's why my brain was breaking, because I was like, how would we use this and what does AUC actually mean? It's the percent of time we give the yes class a higher probability than the no class. Does that make sense? It also goes to correctly ordering them, but it's like kind of putting your yeses at the top. So we want the yes class to get a higher probability than the no class. Because think about this. We'll bring this way back to the start right here. Because what would it mean to have an AUC of 100% if we're trying to figure out if people have COVID? If we have an AUC of 100%, where are all of our yeses for having COVID? Where would they be if we have an AUC of 100% to go like boop, 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 boop? Where would their probabilities be to have an AUC of 100%? To have an AUC of 100%, the yes classes need to be where? At the top, exactly. So when you think about models that have an AUC of 100%, you can have a model here that would confuse people where the model is something like probabilities of something like 99%, probabilities of 98%, probabilities of 97%, probabilities of 95%, and we will put in 5 points, probability of 90%. What would everything be predicted to be here? And this is really where I want to bring everything back to. Sorry, we're just kind of reviewing. My brain fried itself, but this is the whole point of why we use AUC. I'll talk about this again tomorrow because we're way over time. But look at those probabilities and then look at these classes for them. Yes, no, 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 no. What is the AUC of this model? What is the AUC of this model? What is the AUC of this model right here? 100%. Because 100% of the time, the yes class receives a higher probability than the no class. The Red Bull kicked in. 100% of the time, the yes class receives a higher probability than the no class. That's what it means to have an AUC of 1, is that we have the yes class at the top 100% of the time. Not just that it's at the top, but 100% of the time, the yes class, you can see my brain's actually working right now, because all of a sudden I'm like, yes, this is what we should be saying. But what is the accuracy of this model? What is the accuracy of this model? While the AUC is 100%, there we go. The accuracy of this model is what? The accuracy of this model would be what? What would the accuracy be? There's 5 predictions. What would the accuracy? If we use predictions, exactly. Ahmed, you getting it? Yeah. And that would be it right there. You could go and you could just do mean actual equals predicted. So you could figure out the accuracy just like this. What percent of the time do we accurately predict it? So when you think about it, this is like a question I always bring it back to. We bring it back to like my sister doing real estate. What would she like to focus on? If she has a list of 100,000 possible people in Tennessee she can work with, like she'll drive around, like she has a list of 100,000 possible people. What would it mean for her to optimize her model by who she works with on AUC? What would AUC try to focus on? It's going to try to do what's with the yes classes. Like AUC is going to focus on giving the yes classes what? And try to put them where in the model. Like think about how AUC is helped or hurt by where the yes class is and what AUC will focus on doing. It'll put them first. They'll get the highest probabilities. They'll be at the top of the model. They'll be the ones with the highest probabilities. Because this model right here has an AUC of 1, and now this model has a really horrible AUC. But what happened? Well, so the yes class, that's a 50-50, I think. Let's do it. Let's run it. That looks, yeah, it's 50-50 because it'll go right, right, up, right, right. And then it's yeah. And it'll do 50%. So when we look right here, there it is, and there it is. So it's 50%. And these are things we should be able to understand. This is where I was trying to bring it back to. The practical implications of this is I can see that the yes class, does it make sense? The yes class right here, which there's only one of it, 50% of the time has a higher probability than the no class. We could add in one more so you can see it doesn't have to be just be 1. And we'll just add in another, sure, 97%, doesn't matter. But, and then we would have to add in one more prediction right here. It's predicted to be yes. So right here, I have an empty thing, right? Okay, cool. Now we still get the same graphic because it still works the same way and we still get 50%. Does everybody see that the yes class receives a higher probability than the no class 50% of the time? But what is the accuracy of this model? What is the accuracy of this model? What is the accuracy of this model? This model has an accuracy of what? This model has an accuracy of what? Everything, predicted are, why was that no? Sorry. The accuracy is that, yeah. The accuracy is 2/3. The model accurately predicts 2/3% of the time correctly, and the ROC means that the yes class receives a higher probability than the no class 50% of the time. But you can see that this would have the same here. Pretty easy to see this model has an ROC of 100% and has an accuracy of 66%. So the accuracy is going to be 66% and the ROC is going to be 1 because it goes straight up and the ROC is 1. Does everyone see like how these do different things? Where if you put like the yes class all the way down here, what will this do to the accuracy of this model now? The accuracy was 4.6. So the accuracy was 4.6. That's the accuracy. Now I just moved the yes class. I switched it down there. What will that do to the accuracy? What will that do to the accuracy? Look at the percent of time it matches up. What is the accuracy now? All I did was switch this around from here and here. So it's 4.6, and I'm just going to move this to down here. And what's the accuracy now? It's still 2/3. It's still 4.6. So now if we run this, we still get 4.6. Or because you can call it 2/3 if you want. It's 4.6. It's, you know, does that make sense? 66% of the time, the same. So it's still accurate 66% of the time. But putting the yes class all the way down here at the bottom is really going to hurt the AUC. Because now this yes is 100%, this yes is 50, 50, and this is 0%. So the ROC should be 50%. Let's view it. I think I have it all saved. The ROC should be 50%. And there's the plot, and that does look like 50 because it's symmetric and it's 50%. This is, now my brain's working at 100%. Does everyone, who was able to also see that the ROC for this is 50%? This is a decent test question. I know it took me a moment. I swear I know this. You can watch me do it 20 times last semester. I just forgot how to draw the plot by hand. And don't worry, you don't have to draw that plot by hand. And if we did, I'd give you spots, but I can't do that question online. So other than drawing the plot by hand today, everything I was saying was theoretically accurate. Brian's brain overheated, though, and he was like, I can't remember how to draw the plot by hand. Like yelling. But who here would be able to compute this ROC? Who would be able to compute the ROC? I like small problems on the test that have you like compute the ROC. Could you do it for this? How'd you calculate the AUC again? So if you look at it, you can say this yes class right here. Don't even worry about this. When you look at the AUC, don't even look at the what. I mean, you don't have to look at that. So this yes class right here, I've got them ordered with the probabilities. This probability is associated with this. Does that make sense, Ishan, right there? That this yes is associated with this. Does that make sense? This no has this probability. Everything's good there. Okay, good. So we just know that if you go across this, you can see the probabilities for each of these. So we can see all the probabilities going across. Okay. So what we do now is we say, if you want to do it manually by yourself, you can do the graphic. But if you want to do it yourself, you look at it and say, this yes right here, how often, with only compared to these no's, only look at these no's, what % of the time did this yes receive a higher probability than these no's? What % of the time did that yes receive a higher probability than those no's? And you could do it this way. You could do 2 out of 2. Does that make sense? I'll do it that way. What % of the time did this yes receive a higher probability than those no's? % of the time did that yes receive a higher probability than those no's? Careful, careful, careful. So how many no's are there? You only want to look at this yes and these no's right here. This yes right here related to these no's. This yes right here received a higher probability than these no's what % of the time? Yep, half the time. 1 out of 2 times. What % of the time did this yes receive a higher probability than these no's? What % of the time did that yes receive a higher probability than those no's? The next one right there, which is in the same spot. That yes received a higher probability than those no's. Half the time also. Yep. How about the last one right here? This yes received a higher probability than these no's. This yes right here received a higher probability than the no's. Don't look at the yeses. 0% of the time. How many yeses did we evaluate? 4 yeses, 50%. If you look at kind of averages, it's like half, and then the 0, and that the 1 evaluate to a half when you average them. Yep, that's it right there. And so we could add in another one right here. Let's add in a yes down here. 1,000 points first person to figure out. I could be tricky. I could be so tricky, but I'm not. We'll switch it in a moment. So this one's not nearly as fun. It's not. Oh, it's so easy. Well, we can fix it. It's yeah, we could do. We might do office hours later too. I can answer. We were doing some yesterday, and then Ahmed, feel free to ask. Pretty easy to figure out. If we just use what we have, we can just change it. And so that should be it right there, 40% of the time. And so if we run this, 40%, there you go. And all I did was update what I had written to this. Does that make sense how I quickly was able to update my thing right here because we have a yes all the way down here at the bottom, and then we get an ROC of 40%, and you can see the graphic. And it is actually plotting the 40%. It's not giving me the 60, which is interesting. Well, I didn't flip it. But now you can see 40% is the area under the curve. Can you go over number 8? Yeah, let's do that. Let's see here. Let's hop over to number 8. Who feels like they understand AUC, ROC a little bit better now? That this is the ROC curve, this is the area underneath it, and it's the % of the time the yes class receives a higher probability than the no class, and it helps us kind of sort the probabilities. I know I was going to do this right here. I was going to go ahead and do this, and now the yes is at the top, so it should be 60%. It should be 60%. It should calculate to 60%, I think, right? There we go. Do we have a wrong length? 1, 2, 3, 4, 5, 6, 7. What error is it giving? Length object is not a multiple short of object length. Wait, one object. Let's just run length because I can't see today. 7. 7. What's going on? Oh, warning. Yeah, sure. Oh, because it's saying it's longer. Yeah, whatever. Yeah, and then we can trick it even more by going here and putting in like another 0.99 and another yes. Sorry, I went kind of advanced on this. Like I'm making it weird. You see now it's when we do this right here. That 100%, 50-50. So we have 1, 2, 3, 4, 5, 6. I think this is going to be 66%. Yeah, 66%. Don't worry. If you see what I'm doing here, I'm not ordering them, and then I have to re-put these at the top of the model. So awesome. Yeah, sorry. Thank you everyone that my brain broke and everyone dealing with me. And I went super advanced on this because you don't have to have them in order to do AUC. And you can see the graphic over here. The biggest thing is, once again, you should understand the context of it. You should understand that AUC is the percent of the time the yes class receives a higher probability than the no class. The whole point of it is to make our model ordered in a way that we are trying to put the yes classes to the highest probability. It focuses on giving the yes classes higher probabilities. So that's like the biggest possible thing you should know about AUC is it's focused on the probabilities, and we are trying to get our model to order those probabilities to be as high as they can be. Like the whole goal is to get high probabilities, or the yeses to have the highest probabilities. If you put all your yeses at the top, you're good. Like that's the whole point, to identify the yeses. Basically finding the people with the disease, because that's the whole goal. So if you find the people with the disease, you're good. You find the people who are going to buy, you're good. And let's hop in here. What's the start of it? Is it this one? Is this the one right here? Run the following chunk of code, which will randomly split up the rows. We're going to make a, yep. So I think Carolyn wanted number 8. Is this correct right here? We're going to make a training set right here. Tell me if I'm wrong. Dozer not found. I think dozer's in. Do we have to load it up? We had to load it up. Got to load the environment. Let's see if it loads. Let me go load the dozer. I think it's in the Let's go here to load and downloads and assignment 8. There we go. Has multiple versions. Did we get dozer? What is going on? Why is the world going crazy today? Awesome. I might need to re-download that right there. Let me go make sure I have the right file. And where is it? So this is concepts in predictive analytics. Data file, here's the data file. It is downloading. Let's go to sessions, load workspace, and we want to go to load environment. Let's see if it downloads. Downloads. Okay, now it works. That's what we like. As long as it works, it's good. Okay, and we do it. So what's the whole point of this right here? Once again, we should know what every bit of our code does. What we're doing right here is we're splitting our data into training and holdout. So we're splitting the data into data that we're going to train the model on and data we will test the model on. Run the following chunk of code, which will split it up into rows, 60-40 split, good. Run the command setseed 2019 boot.train, yes. And sort sample right here, size this, replace equals true. This will set the random number seed, then randomly picks row positions with replacements of the train data frame. Print the contents of boot train to the screen. Its output, it's okay to include. This is in your write-up. And you'll see the same positions appear more than once. Good. And some positions don't print at all. Then print to the screen the result of running this right here and explain English what these numbers represent right here. Okay, let's take a look right here. So now we have this right here. What does this mean in English? Just take a look at what you have right here and what you have right here. So we have here what is called boot train, and it says 33333. So what do you think I'll see at the bottom to start for the bottom vector? Can anyone tell me what the bottom vector will start with? What will the bottom vector be? Because the bottom vector has, and we should see that code, there's the boot train, but the bottom vector was minus it. I think we show that right here. So I'm not going to run this code yet, but this code is showing on the screen right here. When I run this code right here, you got it, Jordan, it's going to show 1, 2, 4, 5, 9, 11, 14, 15, 16, 17. So these are the rows that were not selected via the boot train. So the boot train is where we are sampling with replacement. If you look at how the code runs, we are sampling with replacement. So we have replace equals true. So we can sample the same row again and again and again. So you get 3 in here 4 times. You get 6 in here 3 times. You get 7 in here twice. You don't get 9. You don't get 4. You don't get 5. You don't get 1. You don't get 2. So now our holdout right here, the things we're going to kind of see how it works on, are the rows that were not taken for our sample. So we sampled with replacement to create a training, and then the rows we have right here are the ones that were not sampled as one of the values we got with replacement. So does that make sense right there what's going on? This is going to make a pseudo-holdout. Using the results from B, create a data frame called pseudo-train, which are the rows in train that appear in boot train. Create a data frame called pseudo-holdout, which are the rows that appear in this. Do not put in pseudo-train, which contain all the rows in range, that do not put in pseudo-train. Create a data frame called pseudo-holdout, which contains all the rows and trains that do not put in pseudo-train. Yep. Verify that you pass the sanity check by printing to the screen the results of running head this and summary of this. Okay, so one of the easiest ways to do this right here is when we go to the boot train, let's just call this BT, and let's just call this BH. Does everyone see I'm just making some shorthands for these? Does that make sense? These are now objects of what I have right here. So this is going to be a really quick shorthand for me to deal with these. This is how I like to deal with code. Just make it quick, make it easy, make it work. So we've stored these objects into something smaller so that I can just handle them a lot quicker. So when we do this, we're going to go to our data frame, create a data frame called this, which are the rows in the train. So we need a pseudo train that appear in the boot train. So now when we do this right here, we're going to go to our train, and inside of the train, we're going to go here to boot train, and these are the rows in the boot train. So we're going to call this pseudo train. Should do it right here. We've got sanity checks. There's that. And there's that. Yes, we like it when sanity checks work. But does this make sense what I did by abbreviating my code right here? Is this making sense, Caroline? The reason I can use BT, realize some people might be like, wait, I'm typing BT and it doesn't work, is because up here I took my boot train rows and I stored them into the object BT. So then I can just go down there and say, okay, these are the rows I want. So I went to the row space and I just said, take my boot train rows, which are the rows we identified as the boot train. And then if we want, we can go here to pseudo train and we'll just grab the pseudo holdout and we can overwrite that and we can do this and we've got our pseudo holdout. So now when we go to pseudo holdout, we have that and we can check the pseudo holdout with this and we should get, it looks like the same, there's the max 16. We have to expand the results. And we should, do we really got to expand them that crazy like? Okay, there we go. And we are getting the same results, it looks like. If you look at 12, 12, 12.5, 14, 13.61, 14, but we are able to create this object right here. How's this looking, Caroline? Is it making sense that what we're doing is we're going inside of our training and making a pseudo holdout inside of it, like a fake, not real holdout inside of the train? And we're doing like a bootstrap method. Okay, good. Yes. It's a tricky question. Side note, having sanity checks on the homework, I know. Yeah, and sorry, hopefully every sanity check works perfectly. Please tell me if they don't work. I will try to fix them. And no, I'm glad that you guys are liking this. And thank you so much. Sorry, today's lecture, my head overheated. I really feel bad for that. And the more I kept thinking about that, I was just like, stop thinking about Brian. You got to get back on track. You know how to draw it. You've drawn it tons of times. It's going to work. Using the LM function not trained from caret, fit a multiple regression model predicting price using all the predictors, no interactions on the pseudo train. So we're going to go right here and we're going to make a model. We're going to make the model using price as our y variable. We're going to use all the x's. Data equals, I like space right there. And we're going to just go here and just click pseudo train, drop it in there, then stores predictions in the on the holdout. Okay. This is where people might get confused right here. Warnings. Oh, it's the graphic error. It's not a day if we don't get the graphic error. So when we do predictions, does anyone know the format of making predictions? It is in the notes and we show it some, but it's from 320. So sometimes we expect you to kind of know how to make predictions. How would we make predictions? There's two arguments to when we make predictions using just predict, which predict is used a lot. There's two arguments. The two arguments for predictions are you type predict. Yep. And then we go here to the model. There's the name of your model, which is going to be used. If you just run that, it'll make predictions based on the data it was created from. So this is predictions on the data it was created from. So if you run it with just the model, it'll do that. The second argument, which has no autocomplete, to this day, it does not have an autocomplete. And I hate that. You have to type in new data. Autocomplete doesn't do its thing. Drives me nuts. And then you have to type in the the name of the model you're using. Now, if you notice, the predictions are different. Please note that this predicts on the data it was created from. This predicts on the new data. So now you're saying, use the model I made to predict on new data. And so those are the predictions right here. We're going to call this object this. And then does it want a summary of it to confirm? And there's our summary to confirm. Yes, we've done it. Using the predicted values and calculate the RMSE on the pseudo holdout sample. So I think it basically, is this it? Hint, a vector of the squared errors can be predicted with this. Well, thank you. It's very nice of you. So if this is the squared error, I mean, we're so close. I need you guys to help me out. I'm going to do a trick right here. I'm just going to call this squared error. Cool. I'm almost there. Since that's my SE, what do I do to that? It's like, hey, here's your squared error. Because the error is your actual minus your predicted and then squared. So this is the error. So does everyone notice that this is your actual, ooh, that's predicted minus actual. And it doesn't matter. Turns out the same. Wait, it says empty. Oh, what's going on right here? Predicted holdout. There's our prediction. And pseudo holdout wins. Ooh, uh-oh, we have an error. We're not predicting wins. Uh-oh, uh-oh, uh-oh. That's an error. Maybe that's what people are hitting. That's an error. I was like, why are we not getting it? So that's that. Never update the assignments, Brian. You'll make errors. Make sure to change. Yeah, I know. There it is right there. I think that's in the notes. Sorry. I need to. I'm sorry. Busy summer. I'm sorry. No. Yeah, if you look, the object did not create. And what doesn't matter is if you notice as I was saying it, what it should be, technically, is it should be this. But if we do this and go to check, and then we do SE equals SE check, oh well. And then, because we're getting all the squared errors. So yeah, it's a bunch of squared errors. So it's, in truth, it's the actual minus the predicted. So, and that's predicted. So in truth, the error, which is a residual, if you remember back from 201, is residual equals actual minus predicted. So it all goes back to 201. Like I can't state that enough, that like what we do goes back to 201. That when you're finding the squared error, it's the actual minus the predicted. But what do I need to do now that I stored this as squared error, which is going to kind of help me out? Since I've stored this as squared error, how do I get the RMSE? Which, if 320 is here, we were just doing stuff like this today. How do I just change this to RMSE? How would I make that RMSE? It's squared error, but how do I fix it now? Yep, that's it. Just go SQRT, mean, SE. There we go. Just like that. And yeah, so that's how it's doing on the holdout, which is probably overfit. We could look at how it did on the original model with a summary of the original model. It does 22,460 on the original model. Here, let's rerun the code, get it right next to it. And 23,000, that's not that bad. When you look at how well it does on the data it's created from versus the holdout, really not that bad. Does that make sense? Like, it has a typical miss of the price of a bulldozer on the data it was created from of 22,460. The typical miss it has on the pseudo holdout, which was kind of held out, is 23,212. Does that all make sense? Like, RMSE is the typical miss. This is from the data it was created from. This is from the data that was held out. What we could do is we could be really interesting right here and see how it works on the actual holdout. So, I won't do that yet. Yeah, less than 10%. Yeah, what we would do is we should take the ratio of that, and we should go here and see how much larger this is. We'd expect it to work worse, and it's 3% higher. That's not that bad. That's pretty good. And that's what you want when it generalizes to new data. And this is more of an internal check right now. This is more of a validation portion. This is a different way of doing k-fold cross-validation. This is bootstrapping within. Because when you think about this, we're pseudo-holdouting some of our data. So this is an internal check before we test it on new data. Like the actual holdout would have to be if we went and we took and we made predictions on the actual holdout. So now, sure, we can just rerun this. And yeah. And then wait. predicted holdout, and that's the predict. And then we need to go here, and that's pseudo holdouts. This needs to be holdout. There we go. And this is how, wow, that's how it does on, so that's how it does right there on the actual new data, which is very close to how the model did on the data it was created from. So it actually does better on the new data. You gotta be kidding me. Yes, that's that. So, I mean, it does nearly the same. This model it does a little bit better on the actual holdout. So, I mean, this model generalizes just about the same. We explained 55% of the variation, and this model works pretty much just as well on the new data as it does on the data it was created from. Does that make sense, Jordan? That this model, and this is what predictive modeling is. We're totally just doing some numeric predictive modeling right now. That this model that was made on data it was trained on, it typically misses by about $22,460. It explains about 55% of the variation. And when we do it on new data, the typical miss is nearly identical. Like on the new data, it would actually work a tiny bit better, like virtually identical. And this is how you gauge models. This is how you like, oh, my model works, works exactly the same. So what does this tell us? This model will work on new data. It'll work the same as it worked on original data, which is the goal of predictive modeling, is to make a model that generalizes to new data. We don't want to overfit it, and I could probably make an overfit if I really wanted. Now write a for loop that finds the RMSE of models trained on 500 Bootstrap training samples. You've already written almost all the code you need. So outside the loop, do this right here. We have to initialize a vector, set it up so it loops through 500 times. Cool. There's that. Yeah, I know. It's a cool question. I love this question. And that's why it's really hard to, like, I'll update the assignments and I'll make an error. It drives me nuts. Okay. Call it SE. We'll call this RMSE. And then square root, mean, squared error. And so that should, we got the pseudo. And, oh, wait. Predicted holdout. What did I do? Oh, because I've changed what this is. Cool. And wait, argument to binary. What have I done? What did I do to my code? Wait, that's working? Let's slow down. We've got here, I had it all working, Jordan, and then I broke it. Okay, that's the model made from the pseudo train. This is predicting on the pseudo holdout. That might have been the issue. We don't need the summary. This right here is using the predictions on the holdout versus the actual. So this should work. And this right here is this. Wait. So, yeah, wait. This right here was just notes. That was notes. Those weren't objects. Yeah, you're right. Jordan, 1,000 points. You're right. It was just a note I was taking. There was no actual. Oh, because these were objects in my global environment from earlier, but they're not. It was saying they're categorical. So it's saying to me, hey, wait a minute, you've got categorical, you can't do that, because I was just kind of putting a note in there for like how it works. The actual minus predicted is the residual. And so that's got that. And yeah, that's basically got it. So when we go down to here, we're just going to drop in our code in the order it was created. And we're basically there. We are so close. And then we got this right here. We just wrote the skeleton, if you can't tell, the whole skeleton. And here, we're going to remove the set seed probably because that's going to cause issues if not, because we don't want the seed to do the same thing. I'm going to remove the set seed now just so we don't have that, because we don't want that. We should probably set seed at the start of it. Make sure to set seed on the same line as and immediately before the for loop. Yeah. So you can, it should be fine. We could do we can do that. Yeah, okay, cool. So we need it before the for loop, because if we set seed inside the for loop, does that make sense? It'll do the same thing for each one of them. We don't want to set seed in the for loop, or else we'll get the same randomness on all of these. And we need here that we're going to create that object. Where did I lose my object to? It wants us to boot RMSEs. So we'll create it here just before it. And boot RMSEs. That's just a blank object now in the global environment. You can see it right there. And then we've got our for loop, and it wanted 500, did it? And there's that. We're going to make it look nicer by going here and go to code. re-indent lines, and it's just going all around right there. That's cool. And so now we should be almost good. There's only a few things I need to change, and the things I need to change are actually very, very small. What will be my variable called? Classic. What am I going to, you guys know, Jordan, what am I going to call my variable? Just classic. Classic, what will the variable be called? Just like, oh, we always call it. Easiest thing to call it. You know what we're going to call it. I. It's just a placeholder. And it's only going to go in one spot in this code, if I'm thinking correctly. Where will it go? I'll start fixing it. There we go. Where will it go in this code? Pretty obvious now. I've basically shown where it'll go. It'll go right there, because we're going to store into the ith object. So the code only needs to store into that position every time it runs. So yeah, so we're going to store into boot RMSC position I. So every time it runs, it'll store into the first, the second. I think it said 1 through 500. So there's the 500 runs of the code. And I think we've done it. Now it wants us to append this to this. So just helps. It makes it so that when we run the for loop, the randomness will run right before it. So that we run the randomness, then we run the for loop to set the randomness. We run that, we give it a second, and then we take a look. We've done it, I think. So is there sanity checks? So this Bootstrap model is there not sanity checks? It'd be nice if we had sanity checks. How's yours looking, Jordan? How is yours looking right here on your, is that the same thing if you run a summary? I don't know if it says run a summary. Try, yeah, looping over the first 5, make sure it works. Yeah. This is, yep. Report the average value. There we go. Mean standard deviation histogram. Yeah, it'll look normal. This is what's so nice about R right here, is being able to do this, just like to change the code. Are those the values you're getting? Hopefully it is. Should be. If my sometimes it can be because your randomness is set differently, but I think I have the same randomness. Jordan, nice job. Yep, that's got it. And I think it was a kind of a fun problem. I mean, we basically did it. The bootstrap estimation of the generalization error can be found using the caret with method equal boot instead of method equal CV. Yep, versus method equal repeated CV. For reasons that aren't completely clear, people tend to prefer cross-validation instead of bootstrapping approach. Yeah. Yeah, but people use bootstrapping. I've used bootstrapping. It just does it for you. And so it bootstraps random samples, and bootstrapped samples are resampling of your original data. So you get to see an example of bootstrapping. And we don't have this in the caret notes using caret. We don't have method equal boot, but you could just change it to method equal boot. So literally we could go back to where we did the fit control today. So if we go back here to fit control, and there's that. Go back to the start. Up. So we should be able to go here, and we were fitting on ROC for our model. And there's boot. Ooh, with number 5. Maybe that's how many times it does the boot. Oh, it does it there. Okay, then let's go back here to gender. And then here's our model. And let's run it right here. Method gender not found because, oh, we have a different train. We changed our, there were 30 warnings. Sure. And now we get a different thing. I don't know why it's giving the warnings. I should look at those warnings. You always get warnings. There's so many warnings. But now you can see how the accuracy, ooh, no accuracy. What's going on right here? But we are getting, there's the mean. And there's the accuracy. Did I fit on accuracy? Will that not fit? Is that why it got mad? It might have been why it got mad. Can bootstrapping not fit on AUC? Because this is supposed to fit on AUC right now. Might have been what the warnings were, because it's not giving, it's not fitting on, because if we do CV and we do number equals, you know, like 8, why not? We'll go high. And then we rerun this right here, we should get the model fitted. Ooh. Yeah, okay, good. And then we should have, wait, am I just going mad today? What is going on? Fit control equals chain control. Fit control. What is going on? With the how many samples were made there with the train? So, are you talking about the question we were doing right here? We'll go back to this real quick. Are you talking about this right here? Is that what you're talking about, Jordan? Is the Bootstrap method of taking cross-valid with Bootstrap method of the validation? It's not cross-validation; it's Bootstrap validation. So this is an internal validity of the model. Is that what you're wondering about right here? When you use the method boot, which let's go ahead and take a look at that. So let's see the arguments inside of there. So this is under the TR control equals fit control. So it should be question mark fit control. Where's my fit control? Stop being weird, R. There's fit control, question mark fit control. No documentation? Really? Wait. Why am I going? Today is one of those days where we just go mad. TR control. It's TR control. It's an argument inside of a train. That's why. Okay. So predictive modeling. Here we go. And here we go. A list of TR control. See the train control. Here we go. Here's train control. Blah. Look at everything you. Oh my gosh. Here's everything. Here's all the arguments inside of train control, which it looks to recognize it as TR control. So it's train control is the full function we are doing as a function with arguments, because we pretty much manually created 500. And I was just curious. Yeah. So the default is boot. That's interesting. The default method is boot. I did not know that till I took a look at this. Number, if else, it's going to grep. It's going to search through. Grep is like a search. CV method 10 through 5. Okay. Okay, so that's where the number repeats if else. So it's doing an if else inside of here. It's complicated. And then that's coding for oh, and then repeated CV. So is it looking for repeat? It's looking for that. I think that's like open characters right there. I need to get better at my string stuff. And then based on the method, okay. And so method can be boot 632. There's log CV, low CV, repeated CV, CV, boot, all optimized boot. And I think they've added new ones since I last looked at this. So then the number, either the number of folds or the number of resampling iterations. So number is going to be related to the boot. So you see resampling iterations. This right here is related to all of these boots. Does that make sense, Jordan? So the resampling iterations, either you're saying for the folds, for your K folds, anything with CV in it. So if you see CV, this is a cross-validation, and that's going to have a number of folds. So that will tell the number of folds for these, and repeated and low. I don't know low. I don't know that off the top of my head. I don't know what the LOO CV means. I'm thinking least something. Oh, and then there's time slice, adaptive CV, adaptive boot, adaptive. There's people develop so many things. So I see. So number 5 would mean 5 boots. Yep. And repeated right here is for K-folds, cross-validation only. Yep. And that's why you see right here where they write this fold, right? This code right here is going to only identify if in your method. Yes. Okay. So if, okay, good. This makes perfect sense. What this will do is it'll search your method, and if method comes back repeated CV, which they're even giving you typo room, it looks like, because they're doing it this way to, like, if when they search your method, when whatever they look for in your method, if it comes back with repeated CV or variants on it because they're allowing typos, then it'll assign 1 by default. So these are the defaults right here. Remember, if you have the equals, it's the default. So if we have this, if it's not this, it puts it to NA. So, and I think because there's other repeated CVs down here, so adaptive CV, no, there's only one repeated CV, right? So the way this code works right here is with the if else, it looks through the method and it sees if your method, because the grep right here is going to return a true or false. So the grep identifies if within method the phrase this is identified. And so that will do that. And then grep is going to see if CV is within it. And the way grep works is it's going to look for the phrase CV somewhere in this. And if you notice, all of these have CV. And I think grep is not case sensitive. So when it sees CV anywhere in these methods, which we're lucky there's no like optimized voot that has like cove optimized voot. I guess CV is, you know, not going to be in there unless it's CV. And then we go right here. If it finds CV, it's going to do 10, which is the number of default. That's the number of default folds it'll make, because this is the default right here. And if it does not see CV, it's going to do boot. So the number of boots by default is 25. Does that make sense there, Jordan? If I do not enter in a number, it does 25 boot resamples by default. Does that make perfect sense? Because if it sees CV, it'll do 10 folds by default, because this will come back true, and it will assign a value of true to this if-else statement right here. And then if it doesn't see CV, the grep will come back false, and then it'll assign the false value. So it all goes back to knowing how to code, like reading what this does and being like, I mean, it's a lot to read through this and to be like, okay, what does this do here? What does this do here? I don't know what the argument P does. You can go down here and see P for leave out groups of cross validation, the percent training. So, so we can, you can assign the percent to leave out for cross validation, which I guess if it does repeat CV, yeah, that makes sense. For repeated CV, there we go. Search, either grid or random, describing how the tuning parameter grid is determined. So, for a search. Okay, so if you're doing a search method, which we don't really do many search methods in these class. Search method is for like forward, backwards, and mixed method search. So there's different search methods you can do. Initialize window. See, I don't even know what initial window is. There's so many things. Who would have thought? With repeats, if the method is in cross-validation, the default is stored. So when you look at that part of the code right here, with repeats, it just NAs this out and doesn't use it. So if you have something in here that's not repeated CV, it'll do default 1. Like if you do repeated CV and you don't enter in anything, it'll do default 1. Like if you do not enter a value of repeats, but you have repeated CV here, it'll put 1 in for you by default. But if you put like boot, it'll put NA by default, because it'll search. This just searches what your method is. This is like kind of like a string search. It sees if method, and here I'll show you real quick. Watch this. Here we'll do a grep. We should get true on this. So if we go to grep, it's a cool function, and then we go to the pattern we're looking for, like Brian, and then we go to this right here, and we go to I am Brian, and we get here 1, and that tells us the position of it right here. And they're just doing that because if we go equals true, there we go right there. But if we did something like Darren right here, and it should do it case sensitive. Oh, no, we do need it's not returning, so you have to do case sensitive, which they're doing CV here. And see, then these loc CVs are not going to return that. I wonder if they could see these CV, like repeated CV. If you go down here and go for pattern CV and you go to repeated CV, we should get true on this, because that is true. So it's going to return a 1 right here, which is still registered as true. But that is the position technically. So what grep returns is the position of the location in the vector. So if you have a longer vector right here of this, we should get 1, 3. There we go. So grep is a really cool function. It looks for a pattern in a string. And there's other ways to use grep too. You could also take this grep right here. Do I have the delta set? Because it's a really cool set to do that with. Here, I'll show you. Let me get the delta data. I'm going to show you this do for the last little bit here, because it's such a cool function. You have to keep all these functions in your head. We've got tweets to airline. Was it tweets? Airlines? Delta? No. Twitter? Tweets? There's tweets data set. Okay, let me go back in time right here and find this. It's Brian having fun at the end of class, because this is such a cool function if you know the fun stuff you can do with it. All the things we keep in our head. Okay, So it'd be all the way back here. All right, let me look at the files. Still got access to them. Oh. See if I can find this. Sorry, this is like riveting class right now. Maybe I can't find it. Let me see. That downloaded. Let me. I don't want to clear the global environment. Downloads. Did that do it? That was right. Try one more time. Oh, okay. I think I know which one. Is it going to be this one? This one will do it. Diet, dozer. No, not going to find it, it looks like. That is such a... It's like on my other computer, I think. I downloaded that one. Okay, wait. Last try. Okay. This has got to be it. Come on. There, we got it. We got it. We got it. Cool. Are you still here, Jordan? There you go. Yeah, there's partial match. You can do like exact match with grep. Like if you read about how grep works, grep is pattern matching or replacement. So you can like replace with like grep pattern 1, ignore case. It's got all these things right here. So what we can do is we've got this tweet data set right here. And if you look like the text awesome. So here's what I was looking for. So what do? We just print it out. So sorry if anything displays on the screen. These are actual tweets. This is actual Twitter data. So United, by the time I finally got to Dallas, I could have driven with less frustration and cheaper. So what we're going to do is we're going to search this string pattern for things like cheaper or, you know, frustration. Let's look for frustration. So we're going to take the grep as it works. We're going to search for frustration, and we're going to search through the text right here. So what did this do? What is this returning to me right now? This is returning to me the whats of all the whats where people said what. So if you look at what I did, I just saw a tweet and I said, okay, this person was talking about frustration. So where's that a frustration person? So they said, here it is. See that? And then look down here. That right there. So does it make sense what this is returning to me right here? Because now you can go here. And it's called tweets, right? Tweet. And put it right there and go here and run this. The positions where people included frustration in the tweet. Jordan, another 1,000 points. Yes, that's exactly it. And then here's all the tweets. That's the rows. And oh my gosh, wait, did I do it right? Oh my gosh, look at all this data. Yeah, this is everything. And you know what we should do? We should go right here and put in text. So we only want that column. Okay, cool. Here's all the observations. And here's the first one we saw. So now we went and we only returned the tweet people said. By the time I got to Dallas, I could have driven. And this must be a drone. We understand your frustration. Our bag time is working hard to get your bags. Every time my United flight got delayed, this is a big frustration. So guess what we can do? We go here to fun, and we go find tweet. And let's just call this, sure, we'll turn this. And then we go here. We take the text right here, and we call it text. And we just go here and go text. And I think that's got it. We run the function, and we go here to find tweet. And we say, Brian. No? Let's go frustration. No? Let's see. Text. Oh, ha 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 ha. I broke the code because we did. Oh, I know what I did. There we go. And then this needs to be text, right? Sorry. So I'm going to go too quick. There we go. I called two things text. Cool. Find tweet. There we go. And what we could do is we could put in an ignore case inside of here. So the grep, I'm going to change grep to ignore case equals true. So we might get more Brian's now. We could also set this right here to value. And we could say value equals true. So now we have an option. It has a default. Does this make sense what I'm doing here? Like we could search your name, Jordan, and you can see, nope, no one said Jordan. Darren, are there any Darrens in here? Did I break the code? There's no Darrens? There's 4 Brians. And yeah, and so you can just search tweets right here. See there, United in-flight promo. So we could search promo. We should see that one too. And I have ignore case equals true by default. So it doesn't matter if I type PROMO. It'll still find the same set. But then I could put here a false, and we won't get any because promo is spelled so crazily. So it's got the ignore case equals false. But if you have a database of tweets right here, you could say like, let's find refund. And we don't want the ignore case. But you can see, yes, I would like a refund. You could even like find the smaller ones. Cover rental car or refund our ticket. I'll gladly drive 10 hours. The time is stuck. You know, like you could, can we find worst ever? And look at this. 12 calls in the span of 2 days, none of which to speak to someone. Oh, you. Oh, you never know what's going to appear. These are real tweets. These are real tweets. Yep. I know, right? Real tweets. So you can search phrases. You can just, we've made our own search right here. And you could easily make databases right here. Like you could give reports. Like if you have this all as a database, you say, well, couldn't someone just do this themselves? You could say like how many times things are mentioned. You could do like a monthly report with this. And you could just do like the phrase never again was uttered 25 times. And you could do like sentiment analysis on this. You could make like a sentiment report and be like, here's how people feel about this. And, you know, these things, like, especially if you only have like American Airlines, like you could do, if this is at American Airlines, so if that's their handle right here, we also want, so now if we want this, we want it only to be American Airlines. We want to go to this, and it also has to have inside of the rows. So rows that meet this condition, so it's, you know, it's going to be easier. We need to take this outside of here for a moment. So let me see here. grep, text, tweet, these positions right here. And so we should do, okay, good. And then we're going to that column. Okay, got it. So we want the ones that are contained in both. So we don't want set diff. We want the non-set diff. So we want right here, so it needs to be in both. So we do one of these minus their set diff. That's the way to do it. So this right here is we take, and we can take the set diff of these two things. So here's our word. Here's the, this is the text we're searching for. So we want to search for the text American Airlines because that's the airline we want. So the text for the airline is that. And then we want set diff. Set diff is the code, right? There's set diff. So this will tell us things that are not included. Text not found. Oh yeah, because we are, let's just do the never again phrase because we're doing a test version of it. Okay. These are the ones that are not talking about American Airlines. So we now need to take our vector of, we could take the vector of, we take this right here, this vector right here, and we subtract off the set diff. So let's call this difference. And then this right here is the all. And so that's the ones that mention it, and this is the difference. And then, so diff are those ones that don't mention that. These are all. And so there's only one, because that's all the tweets that say never again. These are the ones that have American Airlines. And I feel like I'm making a mistake here. So let me look at set diff real quick. The difference in the set, this is all the people say never again. And then the one right here, if this is a set difference, well, that's the only American Airline ones, I think, right? No. I see American Airlines. There's U.S. Airways. Okay, there's a bunch of JetBlue. So wait a minute. Is SetDiff already giving it 1, 2, 3, 4, 5, 6, 7? There's 7 there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's US Airways. What am I doing? 1, 2, 3, 4, 5, 5. That can't be. Oh, wait, there we go. 6. And then that might. Wait. Oh my gosh, what's going on? Brain broke again. Let me see. I'm going to figure this out, then I'm going to hop offline here. I'm just having some fun coding for a moment. Set difference should tell us the difference between the sets. These would all be tweets right here. The positions of the tweet where people say never again. Those are the positions of the tweets where people say never again. And were those the tweets I was showing right here? These were not never again tweets. That's why I got confused. These are all the tweets where people say never again. These are all the tweets where people say American Air, which is a ton. And the difference between the sets, set diff, which seems way too big right here. Does not set diff not do what I thought it would do? Close parentheses. Couldn't find set diff. One, two, three. Oh, it's doing it on the first one, which might be what we want. So this would be things, but we don't want, yeah, this might actually be doing it because this will take out, it goes from 1, 2, 3, and then it'll subtract off the things, because we actually want these numbers right here. So then we want to take, so when we do this, these are our never again tweets. These are our, this is the airline. So these right here are the ones that mention American Airlines. So we want to do, once we get this set diff right here, which is the diff, that'll be 4, 5. Excuse me, that'll be 1, 2, 3. But then we want to take from the first. And yeah, that's right. This is all right. This will be just tweets. So this will do it. So this is the name of the airline over here. Cool. And so we should be able to now take this code we have. It looks to be running. And drop the code in here. Here's the phrase of what we want for the text. So this will always be the text. We won't worry about changing the airline. We'll just keep it to an American airline. And then we need to put this back to being text again, because that's going to be augmented by what we input. And then we want to return, and that's the positions. That's the positions. We don't want to return that yet. We had it written before. We want to go to tweets. We want to go inside of, we could do this. We could go to text here. This is another way. And then we could go to the positions we found via all. Because now I'm going to the tweet vector inside of here, and I'm just going to return the positions I found. And then, of course, since it's a function, we want to go here to return. And now we should be able to find tweets to only American Airline by putting text into here. If we did it, let's see. Let's go to find tweet. And we should only get tweets that were given to American Airline that say horrible. So we should only get American, yeah, look at that. There we go. We have now, we could change it. So there you go. 2 hours on hold, still no answer, horrible. Let's say this. Let's say bad flight. Phrase bad flight. Nope. Flight. Did I misspell flight? There are tons of tweets on flight. Canceled flight. So you could do canceled flight right here. No one said bad flight. No one had a bad flight. There you go. Let's cancel flight. Can you guys help? And then we have 20 rows omitted. But if you notice, and we could, if you want to change your airline name, you could go here and you could say airline, and then you could go here and go airline equals American Airline by default. And now it's going to still do the same thing, but if you wanted to change your airline, you could just go here and go Delta. And we should put, ignore case. We got ignore case on that. Good. And so there's the, whoa. Do we not have, uh-oh, we're still getting American Airlines. I might just, wait, because, oh, haha, wait. Delta, airline, airline. Airline equals airline. Oh, well, might just ignore that for a moment. It broke me. That's why you test your code while you work it. Text, tweet. I will continue on. I'll figure out what's going on. I just, here, give me 2 more seconds on this. Canceled flight. So it's American Airline by default. Let's put in no default for it. Let's do airline, and that is the airline right there. So it should get mad now if I run this. If I don't put in an airline, it should say like no airline. Yeah, good. That's what I want to say. Let's do airline, go equals, blah, 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 blah. Oh, we are, look, it's doing, oh, it's doing like a, what's it doing? Because we saw things that were not American. Here's American Air. Let's do hello. Hello, American Air. And this is meant to be the airline, but it can be other things. Code's not doing what I want. I know, right? It's, the issue is, see, if we change this to delta right here, we should get like the tweets that say never again to delta. And these are the positions of the tweets. So if we have this right here, we should get positions of the tweets that say never again to delta. So if we go to text and we go inside of here, we should get positions of the tweets. See, we're seeing US Airways, which is confusing me because I said delta. Tweet, text, here we go, grep. I think the set diff is not doing what I want it to do because this is grep delta right here. And the grep delta, these are all tweets that say delta. So if we were to say to tweet $text, and then we go into here, we should only see, you see we're not seeing, oh wait, there it is. Look, it's at delta also. Maybe I was missing that. So those are tweets to delta. And then when we go here, after we do this to the never again, is because grep is doing a partial match on the string, including the characters. Yeah, it might be. It might be like the way it's doing a partial match, which it might be doing some sort of partial match that's taking, you see there's grep, gsub, or character string fixed to be matched in the given character vector, of course. So there's so much to it. A string must be matched as is, overrides all conflicting arguments. So fixed, if we do fixed equals true, then it should be, which we might need to add to this. Let's do fixed. It overrides equals true. Okay, cool. And now we see, so do we see delta in here? See, look, I'm not seeing delta. But see, there's the phrase never again. It's the way I'm computing this code right here has to have the problem, because the tweets right here, the diff, so these are the codes that say, these are the ones that say never again. Let me look at these. These are ones that say never again. Those are the positions that say never again. Okay, yeah. And these are the ones that say delta. So if these are the values that say delta, we're looking at, here, there's a quicker way, because the code I'm writing is find matching, I think I know how to do it, values in strings in our partial string match. P match? No. You know what we need to do? We need to do, oh, it's really gonna, okay, wait. What we should do is we should take the 2 strings, because these are just 2 strings right here. I don't know why I didn't think of this. And we should do, is this contained over here? And so this is going to return back trues and falses. And so this will tell us if those items are contained over there, and you see none of them are. So we're going to go here and go to American. And this one is contained over here. So there's only one tweet that says American. We're going to take off the fixed. And now we get that only the last tweet is contained over there. So only that last tweet from, let's just call these will be logical. And so this is the logical. And these are the positions. And then we want to go to the positions and return back the logicals. And we'll save that as all. And now we get American Airline. So this right here returned it back. Now we can look at these and do a test on this to see if it's working, to see like another tweet that has these values in it. So let's go here and just grab another tweet, drop it in here for a second, run this. We've got US Airways. So now we're going to go back in time and we're going to take and put US Airways over here. And we're going to run this with US Airways to see if we get only the US Airway tweets. So now we only have the US Airways. Okay, so now it's working. Now the code is doing what we want, and it was really a percent and percent. Is the tweet, is the number we find over here contained in US Airways? Does that make sense, Jordan? It goes back to just basic R. There's not a fancy function for it. It's just, is a tweet that says never again contained in an American Airlines, or does that make sense? It makes perfect sense. So that's the logical. This returns back trues and falses. Then I get all the positions of the tweets, and then I just go to where the trues are at. So if you notice, there were 3 positions that will be returned here. So I'm just storing those positions. This is all just basic R practice. And I just try to keep my skills sharp because I'm just making up code right now and just having fun. That's what I do. And this will be what we return. This will be the code. So now that we've got our code written, we're going to go down to here, and we're just going to change it up. So this will be what we return right here. And so since this is what we return, we're going to do the text. The text we search for is this. This is the text we search for, and the airline we search for is this. We could put in a default like Delta. So I could do Delta as the default, and that should work. That should work. So now when we go here, we should get hello to Delta. United. Boom. Oh. There's ways, if you go really advanced, where you could search just the beginning of the string. We could like concatenate the string and have it search only the first. I'm not going to do that right now. Part of me wants to do it. But you could concatenate the string and then do a grep on the first 15 characters of the string. Does that make sense, Jordan? You'd have to do string concatenate. Oh, it wouldn't be that bad. It's string concatenate. Oh, we need the library string package. Need string R, because string R has how to deal with strings. So you need string concatenate. That string, is that not string concatenate? Joins 2 or more. So string truncate, isn't it? String trim. Removes white space. String truncate. Truncates the character string. So the string and the width you want it. So you put in a string right here like this, and you say truncate to 5, and it does the ... after it. So you get 3 dots. So if you want 10 characters, you enter in that. So what you would do then is you would take your tweet text, and does it do it on a whole vector? There you go. There you go. And then you grep that. So so watch this. I mean, we got it now. So we're grepping the truncated string. So we're going to search for this, and we just figured it out. We're going to go here to string truncate, and we're going to truncate this string and only search the first 20 characters of it. So that should fix it. You got to be careful editing the insides of functions, but we won't get that tweet we just found because they didn't mention Delta at the start of it. I flooded the screen with output. But this is just how you think about functions. You think about what could I do to change it. It's just practice. So here's where they mentioned Delta at the end. This should no longer return because I'm only searching the first part of it. I took United here. There we go. And so now let's search hello. We don't get anything. But then we go here and we go to airline equals United, and we do get these right here. So, and we need to make sure that the truncate, that looks long enough there. But does this all make sense? What I did now is I truncated the string I was searching so that it only searches the first 20 characters, because I only want to see if they added us at the beginning. Like they're not saying, I don't know, you could choose. It's like, you could, see, watch this. Oh my gosh. I don't want to do that. Well, you go right here. You go if beginning, then run this code. If beginning, run that code. Else run this code. Wait, let me think. Yeah, no, we only need this. So if it's beginning, so now we go back to here and we go to, I'm just having fun with this. Beginning, that's how I spelled it, equals true. And now I can, so beginning equals true. And remember we had delta before right here. So now we don't find it, but now we go to beginning and we go to false. And now we find it. There we go. We're using logicals inside of here. My code's gotten really long. There's a lot going inside of here. Can it read through that if I do that? I think it can. It did. That makes it look a little nicer right here to read through the percent and percent. Here's where we have the if. So we can go here to this else, and we can do that. And that looks a little bit nicer. Yep, so now the way it greps that phrase is dependent on the if and the else. And this is just how you build functions. So everything you've just witnessed here for the last 30 minutes or so is me just building a function somebody could use to search for airlines, and then they've got the augmentable capabilities. Like my boss says, well, we really want, that we only search like it to be in the first phrase, or we really want it to be like at the end of it, or we want to be mentioned in the middle. Like, well, okay, then we got to write the code that searches only the middle of it. We want the code that only searches the first 20 characters. I could make this augmentable to be the first 10, 20, or how many characters we want. I don't know what happens if we create a longer thing, but that's got it. We are good to go. I don't know, we might do some office hours later, but I will see everybody later. Great job, Jordan. Woo! Created a cool function. Bye, buddy.